Good morning, everyone. We will start in a minute. Dinesh, since you're the only one who's around, if you have any questions, you can ask.
Yeah, Sanatan. Actually, I'm sorry. Like I was speaking with my sister, so
It's okay.
just a minute. Yeah. Hello, Sanatan.
Yeah.
Sorry. So Yeah, the linear regression that we were talked about, right? Like the linear regression is helps to, as I told you earlier, like an explanation when you asked. So it is helps to find the minimum of a curve, and it helps to reduce the errors. And we have seen the classifications, right? So
Correct.
when it comes to the classifications, can you give me in one liner, like, okay, this is the classification will do. If it is a k nearest neighbor, it will gives the nearest predicted values of the data set, and we know how it performs, right? So if it is a classification, can you give me in one liner?
Like, do you want to know what is the loss function there?
uh Loss function.
I didn't get you. Like the question that you mentioned, right? See, linear
Yeah,
regression
okay.
is trying to predict a real valued outcome.
Yeah.
The goal is to predict. You can say a variable which is continuous by nature.
Okay.
Anything which can be in general in the domain of say minus infinity to infinity. Okay, so that
Okay.
is what we have to predict. When you are doing classification, your objective is to predict a discrete outcome. So it
Okay.
could be A or B or C or D or E or F. Okay, so given a set of categories, our objective is to predict what is the category for the given input, what is the class for the given input, in which basket you are going to keep it. Is it going to be A or B or C? Now you can use integer labels, you can use string labels, whatever you prefer.
Okay.
So the
So
output is not continuous anymore.
okay, so if it is discrete, like
Let's say 1 or
that
2 or 3 or 4.
okay, so it cannot be like 0, 1 like that.
Now it cannot be both the labels at the same time.
Okay, so it can be any one label.
It can be any one label. If you're doing
Okay.
binary, we typically say it is either 0 or 1.
Okay. Okay. Fine.
Or, so binary means there are two categories. If you have more than two categories, it could be 0, 1, 2, 1, 2, 3,
Okay.
ABC. Okay, high, medium, low. So it
Okay.
depends on what the domain is and what are the categories defined for it.
Okay.
Okay. Do you guys want me to wait for a few more minutes since you two are the only ones around? You and Shilpa? What do you
We'll
prefer?
wait.
Let's wait for 2 more minutes. Meanwhile, if you have anything to discuss, you can do that.
And like it's not related to this machine learning that much. Like if I'm for example, like I'm going to an interview, and in that interview, like the jobs will be, uh, excuse me. So the jobs will, like, if I'm going to ML related, I supposed to have a lot of knowledge in ML, or else if I'm going as an data analyst or a data scientist, on that time also I should have a ML knowledge more, or
Significant knowledge, yeah.
uh,
Yes, you need it.
okay. So whatever the domain I'm going in, like maybe I'm a data analyst or a data scientist, wherever I'll go, I need the machine learning.
Not in data analyst, not much. It
Okay.
depends. It depends on like the company. It depends
Yeah, true,
on
true,
the
true.
job
Okay.
role. It depends on what kind of work you'll be assigned. So they will
Okay.
evaluate you on that. So if you read the JD, right, job description,
Okay.
there it will be clearly mentioned this is what they're looking for, and they will
Okay.
evaluate you for that, not the other
Okay.
skills. I mean, if they intend to hire you for the other skills, then they will
Mhm.
evaluate you on that also.
Okay.
But mostly, you should be like very thorough with the JD and the skills mentioned there. Okay.
Okay.
All right. I see a few people have joined. All right. Let's start.
Nani, I have one question.
Yes. Yeah. Go on.
You made a statement that in
Shilpa, your voice is very low. Just can you check from your side if it's
is it fine now?
slightly better?
Okay, I'll be a little louder.
Yeah, this is fine now.
I was saying yesterday you made a statement that in K nearest neighbors, we do not minimize the loss.
Correct.
We go for the minimum distance.
Absolutely right.
So, but that distance also we select based on
It is a
whichever
fixed distance. Am I minimizing anything?
distance
I'm choosing. See, there are two things. Okay. Let's say I am looking at, so let's say we are 5 friends. Okay. We are sitting on a table. And I'm asking you which of the 2 friends or which of the 2 pairs, okay, are the closest to each other. Am I minimizing anything, or am I just looking at the distances between all possible pairs? And then I'm looking at the distance, which is the minimum.
Just looking at whichever is the
minimum. That is what K nearest neighbor does. Assume that given a test sample, you are going to make a pair with every possible training sample, right? And then you're looking at the distances with respect to everybody. Whichever samples are the closest, you are going to make a decision based on those. So if you choose the number as K, you look at the K closest samples, and then you do majority vote or weighted aggregation, whatever you think is the most appropriate in that domain. Okay, I'm not minimizing anything. Please keep that in mind. Minimizing means that, so let's maybe talk with respect to linear regression, because that's the only thing that you have seen, right, so far, where you minimize something.
Yes.
Okay. So there you had this objective function, which was yi minus yi hat whole square.
Yes.
Okay. Here, yi hat kept on changing.
Correct. Yes.
Yes or no? That kept on changing. Yi hat is a function of the thetas.
Yeah.
So you're trying to find those optimal thetas, which led to the minimum sum of the square differences.
Yes.
So that is where you're minimizing this function, right? And finding the optimal thetas. Okay, let me ask you this. So thetas in linear regression were the parameters, right?
Yes.
Okay. Are there any hyperparameters in simple linear regression?
No.
No, right? Okay. Are there any parameters in K nearest neighbors?
Yes.
No.
Parameters?
See, my question, I'm not trying to confuse you or anything.
Yeah.
Are there any parameters in K nearest neighbors?
No.
No, right? There are hyperparameters too.
Yes.
You need to understand, like, there is a key difference between hyperparameters and parameters.
Yeah, got it.
Parameters are something that are tuned with the help of an optimization technique.
Yes.
Okay. Yes. Or you are trying to minimize a loss function with respect to which the parameters would be specified.
Yes.
Okay. Hyperparameters are those entities which you manually tune. So you will give a range of those values in which you want to search. And then you will try for each combination, or maybe you will try a subset of the combinations and give me those, give me that particular set, which is giving the best performance.
Yes.
Okay. So I can definitely say that k nearest neighbors is a non-parametric algorithm.
Yes.
Okay. However, linear regression is a parametric algorithm.
Yes.
Okay. Now, today we are going to see some parametric algorithms in classification also. So far I have only seen what k nearest neighbors, right? Which is non-parametric in the case of classification and even regression.
Okay.
And we are not minimizing anything as of now. Okay. Today we will see some loss functions that we will try to minimize. Okay.
Okay.
But any loss function that you see in machine learning, in the context of supervised learning, where we are doing regression and classification, you will be trying to minimize with respect to the actual and the output values, predicted output values. The formula that you will see for the loss function, right? It will somehow try to measure the difference between the actual and the predicted in some way. Okay.
Yes.
And the way we are trying to measure this difference, what are the ideal properties that we need? For the loss function that is measuring the error, right? We talked about this. What are the properties that we desire so that we get a good solution at a quick, a unique solution? So what kind of loss function would that be? Think.
A convex differential.
Convex function is something which we require, right? So we get a unique solution.
Yes.
And we get only one minima.
Yes.
We don't have to search if you are using techniques like gradient descent. You will always converge to that global minima, it is guaranteed. Another is, if it is not differentiable, then I can't even use gradient descent.
Yes.
So it has to be differentiable. Okay. We'll keep that in mind, and I'll show you using just those two properties. If you can ensure those two properties, you'll be able to use different loss functions. Okay. And you can minimize those to achieve your thetas, the parameters.
Okay.
Okay. Make sense?
Yes.
All right. Okay. So yesterday we saw some evaluation metrics during probably say the last 1 hour of the class. So there is one more metric which is remaining, which I'm going to cover probably, if time permits, I'll cover it today or tomorrow. I don't want to do it right now because it's a little complex. Okay. And if I do it right away, then many of you will lose interest. Okay. So if time permits, I'll cover it today itself at the end of maybe in the last half an hour, because it requires at least 20 minutes to discuss that. And so right now we are going to see a new algorithm, and then we will try to tackle all the possible, you can say, problems with it and how it can be tuned for different scenarios. So let me make a small data set. Let's say it has 2 features. You can think of having age and height as features. And we are trying to determine if somebody has, just give me a moment, please. So we are trying to use these 2 features to determine if someone is, say, obese or not. So obese is 1, not as 0. Okay, healthy people are 0. Okay. Now, I'll have some samples. Let's say these samples are A1, A2, say 0, B1, B2, say 1, and so on. Okay, so you have a lot of these samples. I'm just going to draw this scatter plot that we discussed yesterday. So we have a 2-dimensional, figure where we have 2 features, x1 and x2. This is age and this is height. And what we'll do is, if you look at this A1, A2, okay, if it is a 0, I'm going to label it maybe say as a cross. Okay, if it is a 0, I'll label it as a cross. If it is a 1, I'll label it as a triangle. So I have some crosses, I have some triangles. Okay, let's say this is the scenario. This is the scenario. This is the scenario that is given to us. Now, what k-nearest neighbor does is this. So I give you this sample. Let's say this Z1, Z2. Okay, so this is Z1 and say this is Z2. Can you see that I have not drawn any X or triangle here? Yes or no? I have not drawn any X or triangle here because I want to determine what is it? Is it X or a triangle? Is the person obese or not? So just by looking at it visually, what can you say about it?
Not obese.
Not obese, right? X's are zeros. Okay. So the idea of k nearest neighbors is let's find the closest samples. So if I'm trying to find, say, the 5 closest samples, I hope you agree with me when I say the 5 closest samples, these must be the 5 closest samples. Okay. Maybe these 5. Yes or no?
Yes.
Okay. If these are the 5 closest samples, let's go by the majority vote. Which are the, what do these 5 samples have the majority as?
0.
Not
0,
obese.
X, right?
Yeah.
Non-obese. Okay.
Yeah.
So that's how you can say, okay, this is what it is. And then you can use the distances to do weighted majority voting that we saw yesterday as well. Look at the distances of each of the samples and give more importance to those samples which are nearby. Okay. That you can also do. So the idea of k nearest neighbors is simply this: look at the closest neighbors and do a majority or weighted majority from that. Okay. Now we are going to see a new idea today. Okay. The new idea is, see, obviously we have to talk about what type of distance that we are using, because we are now in a 2-dimensional space, right? We are in a vector space. So you can think of using different similarity measures, different distance metrics. For example, cosine, similarity, Euclidean, Manhattan, Chebyshev, whatever comes to your mind, whichever you feel is relevant in your domain. You can think of doing weighted or non-weighted voting, like simple averaging. I should call it majority, not averaging. And then you can also think of the third thing. What is that? Number of neighbors. You can try tuning the number of neighbors. Okay. And you can find the best model for this given data set. All right. You can do k-fold cross validation. Steps remain the same, but you have to decide, okay, what evaluation metric would you use? And we discussed some of those yesterday. So you can use accuracy, you can use precision, recall for any particular class. You can define that and you'll be able to use that. Okay. All right. We will see all of that today. However, let's try to first finish some of the other algorithms. So you see a stark difference between the two, the k nearest neighbor strategy and something else. Okay. Let's say this is the idea. This is the idea. Okay. I want to figure out for Z1, Z2, if it is an X or a triangle. Now, don't think of this nearest neighbors. Okay. I'll probably pose a question. So by looking at this, do you think I can draw a line to separate X's and triangles? Do you think I can draw a line to separate X's and triangles?
Yes.
Yes. Yeah. Okay. So where have you seen that line being drawn? In what algorithm you have seen? You typically draw a line in 2 dimensions. Linear regression, right? I hope you remember. I mean, we draw a line which best adapts to the data points. Okay. But is the idea the same here? Just a second, please. Sorry for the inconvenience, guys. Okay. So we have seen one algorithm where we typically fit a line and in 2 dimensions, and our objective is to ensure that this line is closest to the points. Okay. Now, do you think that holds true here? The line that we are going to draw here, is it going to be close to all the points, or is it going to be is it going to ensure that the points are far away and it is also a good separator?
Yes.
It's the other way around, right? It's not the same thing that you have studied earlier. The analogy is very, very different here. I mean, the contrast, there is so much contrast here if you think about it. See, our objective here is, let's try to find a line beyond which, above which, all of it has to be triangles, and below which all of it has to be x's. Okay. Now, let's try to answer some of the simple questions. Let's say if there was a triangle here. Do you think this triangle will ever be correctly classified?
No.
No.
No, right? It's not possible. So if the data is clearly separable with the help of a line, so with the help of a linear function. So if you think about in 3 dimensions, what would I draw in 3 dimensions as a linear function? A plane. A plane. And in 1 dimension, what would be that?
A point or
A
something.
point. Absolutely right. Spot on. And if you think about in 4 dimension, I would draw a 4-dimensional hyperplane, which I cannot draw because I don't know how to do it in 4 dimensions. Okay. Because you are bound by 3 dimensions, right? But some people can really think in 4 dimensions and beyond also. Okay. But it's our limitation that we cannot draw those in like beyond 4 dimensions. Okay. I mean, beyond 3 dimensions, I should say. So the idea here is, if the data set is well separable, yes, you can easily find a curve which can give you 100% accurately, 100% accuracy. All the points would be correctly classified. Okay. But if the data set is non-linearly separable, do you think that a line is sufficient?
No.
Okay. My next question is, if the line is not sufficient and you cannot even visualize like in more than 3 dimensions, so how do you identify which curve to draw?
Then maybe a parabola.
No, then you have to try with different curves, right? Different degrees. Degree 2, degree 3, degree 4. Yes or no?
Yes.
It's the same thing that you did in linear regression. How do I know which degree fits best if you cannot visualize the data? The only thing that you can do is try, right? And see which degree curve gives you the best results. So here also you can try for different degree separators. You can think of line, parabola, you can say a S-shaped curve, which is like a cubic curve, and so on. Okay, you just have to try. You just have to try. If you cannot look at the data and make a decision about it. Okay. Typically, more than 3 features are there in most data sets. So we have to try. Okay. Keep that in mind. It's not that I can tell you upfront, okay, this is a linearly separable data set and go with a simple linear function. You have to evaluate. Okay. So please note that if the data set is clearly separable, there is a terminology that people use which is called as linearly separable. Now, note this, I can only talk about linear separability if I can see the data. Okay. If I cannot see it, then how will I claim it? I can only claim it if I fit a linear function, I get 100% accuracy. If everything is correctly classified in the training set, then I can make such a claim, right? The data set was linearly separable. If I'm not getting 100% accuracy with the linear function, then probably it's not well separated. I mean, the data cannot be separated with the linear function. Okay. So linear separability is when the data set is perfectly separable. Now, what do you think most data sets will be? Linearly separable or not?
Not.
No, never, never, ever. Okay. Most data sets will be highly non-linearly separable. I mean, they will be highly, what we say is noisy. Okay. You will see a mixture of the points like being embedded in, I mean, there'll be like, it's like a coagulation happening between the points. Okay. So we have to find a good curve. That's what the idea is. But let's start with the simplest scenario. Assume, okay, the data set is linearly separable. And let's try to, come up with the simplest algorithm, and then we will try to tune upon it. We already know how to do that. Okay. If you want a parabolic curve, what do?
Take the square of the
Take the squares of the features. Make all possible pairs if you have multiple features. Okay. Take the squares and include all possible pairs also. So if you want, let's say a cubic curve, you want all possible cubes. You want one single and the other pair to be squared. So all those features can be generated. Okay. And you can just train a model on that. Okay. Just the data set would change and nothing special. Let's try to understand how to determine any curve. Okay. I'm going to start with a simple linear line. Now that I have 2 dimensions, okay. Now that I have 2 dimensions, so my thetas would be how many? Now that I have 2 dimensions, how many thetas will be there?
total 3 thetas.
3 thetas. Theta naught, theta 1, and theta 2. So theta 1 for x1 and theta 2 for x2. Theta naught is the intercept term. Okay. All right. So do you want me to go to the nitty-gritties, or do you want me to just explain, okay, use this and you will get your thetas? Tell me, please.
Details.
Okay, details. All right. Okay. Let's see this. Okay. So since we are doing classification right now, okay, our objective is to find a discrete category, a discrete outcome for every value. Okay. But let's forget what we are trying to do. Okay, let's forget what we are trying to do. You guys know regression, right? Okay. Now, if you are doing regression, what is it that we minimize? We minimize this, right? Yi minus yi hat whole square. Okay. And what would be yi hat for this case?
Theta 1 x1 plus theta 2 x2 plus theta naught.
This would be it, right? For this given data set. If I'm going to find a linear, so see, please note that this is not this line, okay? This is not this line. This is not this line, okay? So essentially what I'm doing right now is, I'm trying to find this line. Listen to me very, very carefully. What I'm saying is, in the 2 dimensions, let's try to simply find out a line which is the closest to all the points. Okay, let's try to find that first. And then I'll show you how to find the separator. Okay, then I'll show you how to find the separator. Okay, let's talk about that. Okay. Now my question is, treat your actual outputs. What are the actual outputs right now? What are the possibilities for it?
0 and 1.
0 or 1. Okay, it is either 0 or 1. Okay, let's assume that these are real. Okay, 0 and 1 are numbers, right? I can assume it to be real. Let's assume they are real, and you obtain the thetas by minimizing this equation. You obtain the thetas by minimizing this equation. You can use gradient descent. You can do simple linear regression. You'll be able to obtain one solution. Okay. So I'm going to give you a point. Let's say this is the point which is Z1, Z2. Okay. This is the point which is Z1, Z2. And now I want to know what is my prediction. So what is my equation right now? It's theta naught plus theta 1 x1 plus theta 2 x2. This is the equation that I have, right? I'm going to put Z1 and Z2 in this equation. Z1 in x1 and Z2 in x2. This is what I typically do, right? If I want to predict. Yes or no? Okay, I have a very simple question for all of you. Z1 and Z2 can be anything. Okay. Z1 and Z2 can be any value, right? Along the axis x1 and x2 respectively. Can you tell me what is the range of this function? Theta naught plus theta 1 x1 plus theta 2 x2. In what range it is?
0 to 1.
Why?
Out.
You can put Z1 and Z2 to be anything. See, theta naught, theta 1, theta 2 will be some values that will come out, right? There will be constants once you determine them.
Yes.
Don't you think I can put Z1, Z2 to be anything and you can get minus infinity?
Okay, theta. I thought range of y's.
No. I'm talking about the range of y hat only. I'm talking about the range of y hat only. What is the predicted range? What value can come out? It can
infinity.
Minus infinity to infinity, right?
Plus infinity to minus infinity.
That would be the range, right? I hope everyone gets this. Okay. So regression actually gives us a real valued outcome as the output. Okay. See, that's why I said forget about what you're doing. Your purpose is to do classification. I will talk about that, how to do it. But let's try to see from the perspective of linear regression first. So this algorithm has a very close relationship with linear regression. Okay. So I put Z1 and Z2 in this and I get between minus infinity to infinity. Okay. Now I have a simple question. If I give you a point, okay, if I give you a point which was already in the training data set, let's say I give you this point, which is this A1, A2. Okay, this is A1, A2. If this function did a good job, okay, if this function did a good job, you obtained some thetas from it. If I put A1, A2 in this, what do you think this function should output for this A1, A2?
The actual y.
What is that?
0.
0, right? I hope you get it, okay? Or it should be a value which is very, very close to 0, right? Yes or no?
Yes.
Is it possible that it will, for different values of these x's, do you think for all of them it will give us 0? The line is not passing through the points, right?
Yes.
No. So it will be very, very close to 0, right? For all these x's, if this function did a good job. Yes or no?
Yes.
I hope you get it, okay? All right. So for all the x's, if I put, this function would give me a value which is very, very close to 0, okay? And let's say what about the triangles? So if you look at the triangle input, let's say this is say some b1 comma b2, this is b1 and this is say b2. What about b1 comma b2 if I put in x1 and x2 respectively? What should be the value which is generated closer to
2, 1.
1? Now think about this. Now I am giving you a point which is say z1 comma z2 for which we have to predict. So anything which was an x should be closer to 0. Anything which was a triangle should be closer to 1. Can you tell me the value this y hat, whatever this y hat generates? Let's think of something, okay? If this value is greater than some threshold, I'm going to say it belongs to class, you can say triangle, which is class 1. Otherwise, if it is say class 0 or rather class x, what should be this threshold? That's the question.
Maybe the center of 0 and 1.
What is that?
0.5.
You have the answer. So do you think that with one simple modification to linear regression, I can use it? What did I just say? See, if you have digested this fact, you have seen the first classification algorithm where you are minimizing some loss function. See, all I'm saying is I'm using the concept of linear regression to determine some thetas. Okay, I know that for all the x's which were actually say zeros. Okay, if I put any of those x's in my equation, the value that I will see is very, very close to 0. If this function did a good job, this loss function did a good job of minimization. Hopefully it did, right? Because we are trying to find the minimum value of this function. The thetas should be such that for any of the x's, the value should be 0. Theta should be such that for any of the triangles, the value should be equal to 1. I'm not saying it will perfectly be equal to 1 and perfectly equal to 0. Why? Because the line is not passing through all the points, right? If the line passed through all the triangles, for all the triangles, it will exactly be equal to 1. If the line passed through all the x's, for all those x's, it will be exactly equal to 0. Okay, but that is not the case here, right? The points are distributed and you are trying to fit a line to it. Okay. Now the question comes, okay, how do I use it for classification? See, classification is discrete. So all I'm saying is, whatever your query point is, put it in x1 and x2. And if the value comes out to be greater than 0.5, you say it is class 1, otherwise it's class 0. Because in the middle of 1 and 0, what lies? 0.5 at the middle. So is the algorithm clear? Like a very simple algorithm. You can use the concept of linear regression for classification. This is very simple, using linear regression for classification, but it has so many problems. Okay.
So if I say I do the prediction similar as I do in regression, exactly the same way I predict the values and then compare the predicted value with some threshold.
Threshold.
To classify them in
Yes.
different classes.
Okay. Now there is a big problem. Okay. I'm going to talk about the problems right now. Okay. You can use this algorithm for classification. Okay. It's a decent algorithm. It will work decently. Assuming the data is linearly separated. No, do you think you can draw curves from it? From this function? Do you think you can make a parabola out of it? You can, by the way. You just have more thetas.
Yes.
Have more features, x1 squared, x2 squared, x1, x2. Put it in your data, you'll get more thetas and you'll be able to make a parabola. And if the equation of the parabola, if it is greater than 0.5, so theta naught plus theta 1 x1 plus theta 2 x2 plus theta 3 x1 squared plus theta 4 x1 x2 plus theta 5 x2 squared. If this is greater than 0.5, then it is a triangle, otherwise it is an x. Condition remains the same. You just generate more features. You can do it for a cubic function. You can say quaternary function power 4 and so on. Okay. Very as simple as that. Just generate more features and you can fit different types of curves. But still this has a big problem. Okay. Not a problem, but there is a limitation, I would say. There are also problems, by the way, which probably I will not discuss in that detail. Okay, let's talk about this. Okay. If you think about this algorithm, can it tackle more than 2 classes?
Yes.
How?
If I suppose if I have 0, 1, and 2,
Okay.
and I get my first would be 0.5, the second separator would be maybe 1.5. So if my
Okay, think about this. Okay, let me ask you this. Are you thinking that one threshold would be able to, I mean, the same threshold would be able to do it for the other also? Why are you restraining all the triangles from this range to this range only? If there is another class, let's say 2, don't you think that you just restrained the triangles in a very short range?
yes,
Look at the ranges for what would be the outcomes then? Think about the test set. What would then most of the samples be predicted as?
triangles.
No, they would be predicted as either your class 0 or class 2.
So now if I have like right now I have one threshold at 0.5, which is the midpoint of
Think like anything which is from -infinity to 0.5, what is that predicted as?
x.
Now you create more thresholds. So between 0.5 and 1.5, what is that predicted as?
Triangle.
Now, how big is that range?
Very small.
In comparison to an infinite 2 ranges.
Yes.
So what would everything be predicted as? Triangles will never ever be the case.
Yes. Okay.
So what happens is 2 classes will be masked.
Yes.
Sorry, 2 classes will mask the third class.
Yes.
Okay. See, essentially what we are doing is, see, I'm on this line that I fit, right? I'm trying to find that particular value which is equal to 0.5. So if you give me such a point, let's say this point is say m1, m2. If I put this point on this line and I get equal to 0.5, okay, and I get equal to 0.5, what do you think that implies? Let's say I put a value m1, m2, okay, I put a value m1, m2, okay, or rather, let me just make it like this, okay. So when you did linear regression, you found this line, right? When you did linear regression, you found this line. The equation of this line is theta naught plus theta 1 x1 plus theta 2 x2. Does that make sense? First of all, that is what you found. This is your y hat, okay. This is the line that you found. Okay, I'm going to show you how to do classification. Okay, from this. See, pictorially, what we are doing is, can I say that for all the points that I put in x1, x2, if I get equal to 0.5, so see, I'll repeat this. Okay, let's say I'm going to put some value m1 here and m2 here.
Okay.
Okay, if I put some m1, m2, okay, in this, and I get equal to 0.5. Do you think that can be served as a separator?
No.
Why not?
But
At 0.5, what would you say? Is it 0 or 1?
that's what, like, how will I classify the points which are exactly on the line?
Then there is a tie, right? It's like saying that you are not very confident on the left or the right. Now it becomes your call, like how to break the tie. You are the boss.
Okay.
Okay, I mean, you have to go in one direction, right? You cannot just leave anything. But since we specified the threshold to be 0.5, can I say that wherever the answer is 0.5, okay, let me show you for 2 points. Okay, let's say I feed this point. Okay, this is n1, n2. If I feed n1 in x1 and n2 in x2, okay, I get the value as 0.5. Can I say that for this point I cannot justify that it is XOR triangle?
Yes.
Okay, and there is this point which is say m1, m2 here. And for this point, I also get the value as equal to 0.5. Do you think I cannot justify is it X or a triangle?
Yes.
Okay, I'm going to connect these two. I'm going to connect these two. So I just connected these 2 points where I cannot identify, okay, if it is greater than 0.5, I mean, essentially to which class it belongs to. So what should be the equation of this line? Think about it. Any point which lies on this line, if I substitute in this equation, what this would generate?
0.5.
Equal to 0.5. So can I say the equation of this line is theta naught plus theta 1 x1 plus theta 2 x2 is equal to 0.5? Yes or no?
Yes, yes. Yes.
And this is the line that I intend to find out.
Okay.
Okay. So this is your separator, not the best fit line. Okay. See, best fit line is given to you by regression.
Yes.
We are trying to find that line which is equal to 0.5.
Okay.
So you can say that any point that I choose on this line, if it is equal to 0.5, then I cannot say, right? What was our objective? We want to find the best separator, right? So add the separator. Do you think I should be able to tell is it 0 or 1 if the separator was ideal?
No.
That is the line. Theta naught plus theta 1 x1 plus theta 2 x2 equal to 0.5.
Okay.
Okay. So linear regression gives us the best fit line, which is closest to all the points. Now think about what the other line that we obtained. The other line is actually it is trying to ensure that all x's and triangles, they are far apart.
Yes.
Far apart as possible. Okay. As far apart as possible. Okay. And a few other things that you need to keep in mind. See, when I minimize this function, there is this summation involved. So can I say that every point contributes?
Yes.
In determining the thetas, right? The orientation of this line, every point contributes. Keep that in mind. I'm going to use it slightly in the latter half of this course. Okay. So in linear regression, the decision boundary. So this separating line is also called as a decision boundary. This separating line is also called as a decision boundary. And what is the equation for this?
Theta naught
Plus theta 1 x1 plus theta 2 x2 equal to 0.5. Keep this in mind. Maybe sometimes, like if an interviewer goes in very deep, they can ask you the equation of this line. Okay. If you have d-dimensional data set, theta 3 x3 plus theta 4 x4 plus theta 5 x5 equal to 0.5. Equation will not change. It will be equal to 0.5. Okay. Now let's try to see. So I have shown you one limitation, right? So do you agree with me that it will only work for binary data sets? Okay. Think about this. If I draw a line, it can only separate 2 classes, right?
Yes.
See, the other idea that you gave me, you said I will choose one more threshold. So basically you're saying you'll draw a threshold here, right? A line there. Okay. Which is not the right way to do it, right? Because then the triangles would kind of be masked by the other 2 classes because the range is very small.
Yes. Yes.
Okay. So there is this big problem of masking in linear regression. Okay. I don't want to do that. Okay. So the idea here is, one line can only separate 2 classes. So this is a binary classification algorithm. It cannot separate more than 2 classes. Okay. I'm going to show you some strategies which can help linear regression to be applied to even multi-class data sets. We will talk about those a little later. Okay. Those strategies are also there. So there the idea is you can draw multiple lines, but not on the same data set. You will do something to these data sets first. Okay. So we'll make multiple models there, not one model. Okay. We'll talk about that a little later though. Now, so you have seen how to do this classification with the help of linear regression.
And one more thing over here, like yesterday you told that some of the machine learning algorithms for binary, they use -1 and 1.
I'll talk about those as well. Don't worry, I'll talk about those as well. Not the right time.
Okay.
Should I tell you the name of the algorithm which uses it? Support vector machines.
So in that case, the separator line equation will be equal to 0 rather than 0.5.
You are so smart. Yes, it is equal to 0 there. Okay. I'm going to change this algorithm now, and there also it will come down to be equal to 0. You will see that. Okay. Let's wait for some time. Okay. You are jumping, but spot on. That is what I need from like the learners. Okay. I'm very glad. Okay. You were able to deduce up to that point. Okay. All right. So I don't know. I am very happy. I mean, you got up to that point. Okay. So let's try to understand with this linear regression for classification. This is our separating boundary. Okay. So I've told you one problem, and the one problem is masking. If you choose different thresholds, okay, one class would get masked, and many classes would get masked. Essentially, if you have multiple classes, only the class which is on the top and only the class which is on the bottom, those will be the. I mean, for those classes, you will have good predictions. Other classes will simply be masked. Okay. So I'm not saying no predictions would come, but there will be very limited predictions for those classes. Okay, so your results would be very biased. So that algorithm, this algorithm is not applicable there. Okay. Now let's try to fundamentally understand what do we actually need when we are doing classification. So do you think that if I'm doing binary classification, what should be the ideal property or when I'm going to train an algorithm, what should be the range of the predicted output? If I'm going to train a classification algorithm, what is it that you want essentially? If you were to make your own algorithm, what would you want? What should be the predicted output as? See, currently I did regression, right? The output came out to be between minus infinity to infinity. Okay. But let's say you were to train your own classification algorithm. So what do you want the prediction to be? Do you want the prediction to be just 0 and 1, or do you want the prediction to be, say, between minus infinity to infinity, or between 0 to 1, or between, say, 0 to infinity? What is it that you will desire? Think.
0 to 1.
Between 0 to 1, right? Why? Because if the outcome is between 0 to 1, don't you think I can interpret it as a probability score?
Yes.
And then I would be able to tell for sure that I am, say, 30% confident in favor of class 0 or 70% confident in favor of class 1. Yes or no? Something like that?
Yes.
I would prefer my answers to be constrained in the range of 0 to 1, right? And that will help me determine I hope you remember precision recall and all that by changing different thresholds. Okay. Then I can decide, okay, which model is better. So don't forget the thresholds that we discussed. That is why it is used here. Okay. So ideally, we want our predictions to be in this range, okay, between 0 to 1. So let's say the prediction is coming out to be, say, 0.3. Okay. Assume some prediction comes out to be 0.3. Okay. Can I say that I'm 30%? Okay. So if your prediction is 0.3, what would you say the output is, 0 or 1?
0.
Okay. So what is the threshold that you used?
0.5.
0.5. Okay. So this is the threshold that you used. If it is greater than 0.5, you say it is class 1. Otherwise, you say it is class 0. So for 0.3, it is less than 0.5. So it is class 0. Okay. So instead of writing it as y hat, can I write it as g of y hat? Can I write it as g of y hat instead of writing it as y hat? Just a notation I'm using. See, why am I writing it as g of y hat? Because y hat we typically write as the output for real valued tasks. Okay. So since we are doing classification now, okay, I'm going to show you some magic. Okay, I'm going to show you some magic. Imagine that you give me any number. Okay. So how do I make a prediction using linear regression? What is the function that I use to make a prediction using linear regression?
One feature.
Two features, that the one that we are using. This is the one, right? Yes or no? This is the function that I use to make my predictions, right? Okay, and what is the range of this?
Minus
infinity to plus infinity.
Correct. Okay, now I'm going to do some magic on this and see the magic. Okay, let's apply some function on this y hat, which is nothing but g of theta naught plus theta 1 x1 plus theta 2 x2. And let's ensure that if whatever value is generated by theta naught plus theta 1 x1 plus theta 2 x2, it should be now squished between 0 to 1. Then my job is done, right?
Yes. Yes.
Okay. So can you think of any such function which can do it?
Normalization.
No. In normalization, what is it that we are doing? We are looking at the other values also, right?
Yes.
Talking about a single value. whatever the single value is, which is between minus infinity to infinity, you apply a function on top of it. It now gets squished between 0 to 1. I don't have other predictions. Okay, I'm not normalizing it with respect to other predictions. This is just one value for one sample. And now I want to ensure that if you put it in this equation, it will be now between 0 to 1. Any guesses? Some of you might know this function already. Anyone? These type of questions they might ask, okay, in the interview. Okay, so this is simply actually a maths question. The function is called as the sigmoid. It's called the sigmoid function. Anybody knows what a sigmoid function is? Anybody knows what a sigmoid function is? No?
No.
Defined as 1 divided by 1 plus e to the power of minus z. Okay. Z can be any number between minus infinity to infinity. Essentially, z is, if you think about it, z is nothing but theta naught plus theta 1 x1 plus theta 2 x2. Okay, and so on if you have more features. Okay. What happens if z is infinity? What is g of z? Put z as infinity. What is g of z? Okay, what will this value be? E to the power minus z. If z is infinity,
1.
will it be 1 or something else? Put z as infinity. What is e to the power minus infinity in that case?
E to the power minus.
See, you can write e to the power minus z as 1 divided by e to the power z. Yes or no? This thing can be written as this, right? If z is infinity, e is 2 point something, okay, 2.78, something like that. Okay. 2.78 to the power infinity, what will that number be?
Infinity.
Infinity. 1 by infinity is what?
1 by infinity.
Is 0, right? 1 divided by a very big number is going to tend to 0. Okay. So 1 divided by 1 plus 0 is going to be what? This number becomes 0 when z is infinity. So what is this number, g of z, when z is infinity?
0 only.
1 divided by 1 plus 0.
Okay.
1.
Okay, so 1.
1. Okay. All right. If z is infinity, it converges to 1. What if z is minus infinity?
Zero.
0. Spot on. So e to the power of minus infinity will become e to the power infinity. Infinity plus 1 is infinity. So 1 by infinity is 0. Okay. I hope you get the point. All right. Okay. So I'm going to apply this magical function and now it will give me, okay, now it will give me a value squished between 0 to 1. Okay. So you can use the idea of linear regression, find the real value, apply sigmoid on it, and your job is done. Okay, as simple as that. But this is not as simple. Okay, let's see what are the problems now. Okay, let's see what are the problems now. Okay, okay. Before even, okay, let me describe the problems. So in linear regression, what do you minimize?
Thetas.
You minimize the loss function, where this is the loss function, the squared error, where this is given as this, right? This is what we minimize in linear regression. Now you are doing classification. So don't you think we should minimize with respect to the g of yi hat? Yes or no? What is my predicted output now? It is g of yi hat, right? Yes or no?
Yes.
So, okay, think about this. If y, what is the possible values of yi right now?
0 or 1.
Or 1. Okay. And what is g of yi hat range? Between 0 to 1. Okay. My question is simply this. Let's say if the actual value is 0 and the predicted value is 0, what is the loss?
0.
Okay. If the predicted value is 0 and the actual if the predicted is 0 and the actual is 1, what is the loss?
1.
1. So do you see that there is high loss when I'm moving far away?
Yes.
Okay. Similarly, you can think of the other way around as well. If the actual is 1 and predicted is 0, what is the loss?
1.
1. Okay. So you are still high. I mean, the loss is still high when, you are far away from the predictions. Just keep in mind that, okay, G of I hat is in the range of 0 to 1. This is either 0 or 1. Okay. See, this representation means either 0 or 1. They are discrete categories. Either 0 or 1. Okay. This is between 0 to 1. Okay. Including 0 and 1. Okay. Including 0 and 1. Okay. My question is this now. So if you try to minimize this, okay, if you try to minimize this, so how do we solve it? Let's say this is my loss function now. How do we solve it? I hope you remember linear regression. How do we solve it? And we have studied some techniques, right? How do we solve it? See, one technique that I showed you was you take the derivative of this function with respect to theta naught, equate it to 0, take the derivative of j with respect to theta 1, equate it to 0, take the derivative of this with respect to theta 2, equate it to 0. This is the first technique that we discussed, right? Yes or no?
Yes.
Okay. So this is equation 1. This will give us equation 1. This is equation 2. This is equation 3. Now, I have 3 equations, 3 variables. When can I find the 3 variables, theta naught, theta 1, and theta 2? What should be the type of these equations? If I give you 3 equations, okay, can you solve for any type of 3 equations, or they have to be linear? Okay, do you think that you can solve for x1 and x2? Let's say I'll show you maybe 2 equations. Let's say the equation is like this. Can you solve for these equations? Can you find what is x1 and x2 from these 2 equations?
Yeah.
How?
2 variables and 2 equations means we can solve, right?
How?
Um,
This is a fundamental maths question. How would you solve it?
We can take the differential minus
Differential as in?
for the x1 powers.
Why would I take the differential if I'm telling you these are the 2 equations and I want to determine x1 and x2 from it? Find me a solution of x1 and x2 which satisfy the 2 equations. That's the question. Do you know what type of equations can you solve? They are only linear. Are these equations linear?
No.
They are exponential. They have an exponent term.
okay.
You cannot solve them. Try it out. Okay. Use as much brain as you have. Okay. Try it out. If you're able to eliminate x1, okay. See, the one thing that you can do is this, right? What you will do is you will say 0.5 into e to the power minus x1, 3 minus 4 e of minus 5 x2, right? Yes or no? You will try to write x1 in terms of x2, and then I can say, let's say e to the power minus x1 will be 3 minus 4 e to the power minus 5 x2. Okay. This would be divided by 0.5. Okay. And then you will take log on both sides, log base e on both sides. So you will have log term there and this e term there. Do you think you'll be able to solve it? That's the question. Do you think you'll be able to find a solution when you have a complicated equation where you have logarithm term, you have an exponent term,
No.
and the beauty is, will you be able to take out x1 common? It is in the power, or x2 common. It is the power.
Okay. Yeah, got it.
You will not be able to solve them. Okay, do try it out. Okay, do try it out. Okay, I'll leave this as an exercise. Okay, you try coming up with your own nonlinear equations. As long as you are not able to remove one of the terms, let's say if you are not able to remove x2, you cannot solve for x1. Okay. So only linear equations can be solved. See, you can solve for these type of equations. Maybe like this. Maybe say 6x1 minus 7x2 is equal to 3. You can solve for these type of equations. How? Because they are linear. You can multiply. So you can find x1 in terms of x2. And then you can easily determine. Okay. Or you can multiply this term by 6 and this term by say 3. Okay. And then you can cancel out this x1 and you can determine x2 first and then x1. This is what you have studied, right, in the past.
Yes.
Basic maths. Okay.
Yes, by mistake, actually, that.
No, it's okay. It's okay. See, my job is to help you recall and make you understand why this cannot be solved. Okay. I'm not trying to discourage anyone. Please be interactive as much as you can. I'm not trying to, hurt anyone in any way whatsoever. This is just to help you guys recall why you cannot solve this. So I want you to make you realize when you take the derivative of a function, okay. When I took the derivative of this function, the magic was these were linear equations. In terms of thetas, they were linear equations. Now think of this. You have a g function, and what is g? This g function is g of yi hat is 1 plus e to the power of this minus yi hat. And what is yi hat? Theta naught plus theta 1 x1 I, and so on till, let's say if you have d features, it is theta dx di. Okay. Now my one question is this. There is this exponent term, this e term here, right, in the equation. Now, if you can answer this simple question, what is the derivative of e to the power x? What is the derivative of e to the power x? If you read about differentiation, which I believe I asked you guys to, what is the derivative of this term? Anybody?
Is it same only?
It's the same, e to the power x. So do you realize that you cannot essentially eliminate e to the power x? If you have an exponent term in your equation, when you solve for it, exponent term will not go away. Yes or no? Look at this equation that I will try to take the derivative for. It has an exponent term right now. So even if you take the derivative of an exponent term, exponent will not go away. So the resultant equations will not be linear. They will be exponential. They will be having exponential terms. So you cannot solve it like this. Okay. You cannot solve it like this. Okay. That's the first problem with this way of solving it. So the idea is you cannot use this equation because the derivatives will not give you linear equation. But some of you may ask, sir, I can still use gradient descent. The answer is yes. See, how does gradient descent work? Gradient descent says that the updated value of any parameter is nothing but the old value. This is the updated value. This is the old value. Minus, you can say, eta times the learning rate times the gradient, right? Yes or no? So the idea is I can start with like different values of my thetas initially, and I will keep on updating it. I can compute the gradient, right? Gradient is going to be a scalar quantity. I can compute the gradient, right? Yes or no? Can this gradient not be computed? It's a formula, right? I'm not asking you to determine the values of theta, the optimal values of theta 1, theta 2. But in every iteration, if I tell you what theta is, can you compute the gradient at that value?
Yes.
You can, right? So you can use gradient descent to solve it. There is no harm in it. Okay. However, there is a big problem. The big problem is this function is not convex anymore. This function that I wrote, okay, this squared function which I wrote, okay, this one. When you are using this g of I hat, because of the introduction of exponentials, this function is not convex anymore. So if this function is not convex anymore, what is the problem?
No global minimum.
You might end up in a local minima. So if you end up in a local minima, what could be the issues? You will not get the best performance. Okay. So this function is differentiable, but it is not convex anymore because of this introduction of g. So we should not use gradient descent also on this function. See, when do we prefer gradient descent, if you think about it. If the function is convex, right, and differentiable. Because we get to the best solution possible in that case. We are guaranteed to go down, descend towards the minima, if the learning rate is small. Okay. But that doesn't happen with this because it's a non-convex function. You can think of it like this. This would be how the loss function be. So if you, unfortunately, if you started here for your theta, you will end up here. You will not go to this one, or maybe this one, which is the, the least minima amongst all the local minimas. Okay. So you cannot use, it's not advisable to use gradient descent in this case. So what do we use? Okay. So I am going to tell you some loss functions which are convex. Okay. So I'm going to tell you which are the loss functions that are convex, and then you can use gradient descent on top of it. Okay, let's see that. Okay, this is a little complicated. So I'm going to write the loss function and then we will talk about, okay, do you want me to show the convexity of it as well? Do you want me to show the convexity of it as well? Or do you want me to just tell you, okay, this is a loss function, treat it as convex? Just take my word and say, okay, this is convex. And then you do gradient descent on it and it will work. It will give you the thetas. Do you want me to show the convexity of it?
Yes.
Or, okay, all right. Okay, by the way, this is one property that you can remember. If you want to prove something is convex, okay, so this property will work as long as the function is differentiable. Okay, so if you have a differentiable function, what you do is you take the double derivative of a function. You take the double derivative of a function, and if it is greater than 0 always, the function is convex. Okay, guarantees the function to be convex. For any value of x, if the double derivative is always greater than 0, okay, it guarantees the function to be convex. This is just a check. If you want to, if you are doing this quickly, okay. Now do it for x square. What is the double derivative?
2.
2, and 2 is greater than 0, so you can directly say, okay, this is convex. Okay. All right. Okay. Now I'm going to show you how loss functions are actually designed and how you can ensure that, okay, these functions are convex. Okay. And see, our desirable properties are that the function should be convex and differentiable, so that we can apply gradient descent and we get to the best solution possible. Okay. So the function has to be differentiable also. Okay. And if there is one more property which we can have, for example, if we can get the solution directly in one shot, like the closed form solution. Okay. If we can get that, that would be great. If not, that is, we can still do it with gradient descent. There is no harm in it. Okay. So let's try to understand how to make a loss function. So I'm going to be very, very interactive. Please try to answer my questions, and that way I'll be able to give you more details. Okay. And you can ask me any number of times in between. So what are the possible values for an output when you're doing binary classification for this algorithm? What are the possible values?
0 to 1.
0 and 1 or 1. Okay. 0 or 1. The actual value for any sample is either 0 or 1. Okay. Actually, I'm going to show you two loss functions and then I'm going to combine them. So let's try to make a loss function when the actual value is 1. Okay. When the actual value is 1, I'm going to show you one loss function which can measure how badly you are doing. Okay. Please note that any loss function simply measures. We are trying to come up with a loss function L or J, whatever you want to call it. We have to come up with a loss function that can measure the difference between actual and predicted values across all the samples. Okay. Across all the samples. And our objective is to minimize this loss function. Okay. Our objective is to minimize this loss function. Okay. And the desirable properties that we need, I have talked about this here: convexity and differentiability. Okay. All right. So I'm going to make a plot just to illustrate how these functions are designed. Okay. So what is my output right now? Is it yi hat or g of yi hat? What is my predicted value right now? It's G of I hat, right? It's a sigmoid. Okay. So here you can say this is the predicted value and this is the actual value. Okay. So in this algorithm, I want the sigmoid of the output, sigmoid of a real number. Okay. All right. So let's make a small plot to illustrate something. Okay. So I'm trying to see, I'm trying to come up with a loss function. So let's say this is my loss function L. Okay. I'm trying to come up with the loss function L. Okay. And let's try to see with respect to our predicted value. This is the predicted value. So what is the range of predicted value? Yes, people. What is the range of predicted value?
0 to 1.
0 to 1. Okay. So this value will be now between 0 to 1. Okay. Now I have to design a loss function. Okay. My actual value is 1. Please keep that in mind. This is important. My actual value is 1. Please keep that in mind. So if the actual is 1 and the predicted is 1, what should be the loss?
0.
0, right? So where I have plotted it, do you agree that makes sense?
Yes.
The loss is 0, right? Okay. This is 0. Okay. Let's say this would be somewhere here. Okay. So this is 0. So loss would be here, right? Yes or no? Makes sense? Okay. All right. Now, if I move away, what should be the loss? It should be high or low. So let's say I'm at this point where G of Y I hat is maybe say 0.3. What should be the loss? High or low?
High.
And can I say that the loss should increase if I'm moving away from this value 1?
Yes.
This plot should be like this. Yes or no? So as I'm moving away, the loss increases, right?
Yeah.
Okay. I hope you get the point. Okay. All right. Now I'm just saying this is high. I'm not telling you, okay, what the actual loss will be. Okay. So it should be as high as possible that I can make it out to be. Okay. Similarly, look at the other spectrum. Assume that my actual value is now a 0. So I'm trying to design a loss function for all those samples where the actual value is 0. Okay. So this is your G of yi hat. Okay. This is your G of yi hat. This is between 0 to 1. This is your loss L. Now, can you tell me what should be the loss if you are at prediction which is equal to 0?
0.
Okay. So can I say this will be nothing but the mirror opposite of it?
Yes.
Okay. So if you combine these two, do you see that it comes out to be convex?
Yes.
Yeah.
Absolutely.
Absolutely.
But is it differentiable?
No.
No.
No. It's absolute right.
Okay. So absolute is not differentiable, right? You see that there is a sharp turn if I combine them.
Yeah.
So what can we do? Can we make it like something smooth? And okay, I'll tell you maybe one more. See, currently my loss is actually increasing linearly, right? Yes or no? If you look at the line which I just deleted, my loss is increasing linearly as I move away from the actual value, right?
Yes.
This is a linear line, linear increase. Now I'm going to make it parabolic. I'm going to give more penalty if I'm away from the actual value. So this would be like this. Okay. And the loss is actually infinity when you reach 0. Don't you think that would be like super great? It would be super. If my model does a very bad prediction, the loss is infinite. Yes or no?
Yes.
Yeah.
You're penalizing it more. So it should give you accurate values. So your prediction should be very, very confident. When your actual value is 1, the prediction should be as close as possible to 0.9999999 and maybe very, very close to 1. Okay. That's what you want it to be, right? That's why you're penalizing it very highly as you move away. And similarly, I'll do it for this other way around as well. And don't you see that now? See, my drawing is bad. Okay. I don't know how I made this. Okay. All right. Okay. Okay. But I hope you get the point. Okay. I hope you get the point. Okay. Now, can you visualize, okay, what is happening? Now I'm merging two half of the parabolas. Okay. So smooth. Okay. So this is like this. Okay.
Yeah.
All right. Okay. Now let's see what are these functions though. I haven't talked about these functions, right? Okay. I haven't talked about these functions. What are these functions? Okay. How can I make a function which is like square of it? So, okay, let's think of a function. Can you think of anything which, if you square it up, it goes to infinity? See, this is the function in terms of g of yi hat, right? My x-axis is g of yi hat. Do you know of any such function between 0 to 1, it goes to infinity?
It's a fractional expression.
No, okay, think of, let's say this is x-axis, okay? Let's say I give you a function which is say this x-axis, x is between now 0 to 1. Give me a function at 0, it goes to infinity. At 1, it goes to 0.
1 by x.
Is that so?
Not 1 by x.
No, but is it a parabolic increase? I mean, exponential increase. Is it a parabolic? So think about this. If you say 1 by x, right? I agree.
Yeah.
I'm not denying that. I agree. Okay. But is it a parabolic increase as you go away?
No, sir.
No, it is actually, by the way. You're right.
Yeah.
It's an exponential increase. As you move away, as x decreases, right? 1 by x becomes more and more. Okay. 1 by x
Yeah.
becomes more and more. But is 1 by x? Okay. Think. Okay. Right now, 1 by x is differentiable, right? Yes or no?
Yes, sir.
1 by x is differentiable. I totally agree. 1 by x is differentiable. Okay. But there's a problem with this. Think what the problem is. I want
X is 0.
is convex and differentiability. Yeah, what is the problem?
When x is 0, it's undefined, right?
In-
That is a problem.
In this case, I want it to be undefined. I want it to be very, very high. Okay.
Okay.
I want it to be undefined. And you are right, by the way. I can use this 1 by x also, by the way. Okay. But there's a problem. Think what is the problem? Okay. Maybe I'll define the problem in just a bit. Okay.
Okay.
It will be clear to you. It will be clear to you. Okay. Just a second. Okay. The reason, 1 by x cannot be used, I'll just give it to you in a bit. Let's, okay, think of any other function that you can think of.
Hmm.
Okay, can you think of something which is not defined at 0? Which is defined for negative numbers. 1 by x is defined for negative numbers, right? Yes or no?
Yes, sir.
Okay, 1 by x is defined for negative numbers. Okay. Okay, let's think of something which is not defined for negative numbers, first of all. Any function, not defined for negative numbers? These are the questions that will stump you in the interview. Okay, you should know about these are basic maths questions. Anything that you know which is not defined for negative numbers.
Log. Is it log?
Somebody said something. I think it was correct.
Is it log?
Yeah, it's log. Log is not defined for
Log is
negative
not-
numbers. Spot on.
Yeah,
Okay, let's try to do. So one reason why 1 by x is not preferred. Okay, it's not defined for negative numbers. Okay, log is defined for positive numbers only, and the reason why I'm using log is you will see in just a bit, and it has a very nice property. Yeah. So this is, let's say, your x-axis. I want to draw log of x. Okay, I want to draw log of x. So what is log of 1, by the way?
0.
0. So the function should pass from here, right?
Yeah.
Okay. And is it defined in this negative range
No.
from 0 to minus infinity? No, right? So there will be no plot in that range. Okay. Can you tell me what is, say, log of 0?
Infinity. Log 0 value infinity, right?
Is it infinity or something else? You just missed something. It's infinity, but it's something else.
Undefined.
No, it is minus infinity.
Okay.
Not okay. Okay. Let's take an example. Let's say what is log of any number which is between 0 to 1. Okay. Let's say the base is 2. You can think of base to be 10 also. Any base would work. Any base would work. Okay. Let's say if I give you a number between, say, 0 to 1, let's say the number is 1 by 4. What is this value?
Or something. 2.
Minus 2.
Minus 2, yeah.
Does that
So
make
1 by
sense? 1 by 4 can be written as 1 by 2 square. I can take 2 to the power minus 2. Log 2 of this power will come out. We'll write it like this, and this will come out to be minus 2. Does that make sense?
Yes.
Yes.
Okay. I will make it smaller and smaller. Let's say I make it 1 by 16. What is the output now? Log 2 of 1 by 16?
So minus 2.
Minus 4. Okay. If I make it smaller and smaller, do you see that it is going towards minus infinity?
Yes.
Let's make it 1 by 32, 1 by 64, 1 by 128, and so on. Okay, this is just to demonstrate. As a number converges to 0, you are going towards the value minus infinity. So the curve actually looks like this. Okay, curve actually looks like this. And what do you see? What will happen for positive numbers? Anything which is greater than 1, what do you think? I mean, it is actually like this. Okay. See, my drawing is bad, but I hope you get the point. Okay, like this. Okay. It's a positive parabola now. Okay.
Yeah.
Now, what is my main focus? Up to 0 and 1. Okay. Do you see what is this function that I made? See this. What is this? This function is log x, right? The one that I have made. This is log x. Okay. I just made one function which was very similar to this. What is that function? To the left hand side or the right hand side? This should probably give you an idea. What is that function? Look at this. Okay. At 0, it goes to what? Minus infinity. Okay. Any similar function that you see here, which is the one, left or the right?
Left one,
Okay. But in my case, what does 0 go to?
minus infinity.
No, in my case, look at this. In my case, what does this left hand side go to?
Infinity.
So can I say the function would be minus of log x? And what is my x? G of y I had.
Reflection about the x-axis.
Okay. Do you realize that now? It's like the mirror opposite of on the top. Okay. So do you realize I can use this function? Log is differentiable, right? And you can see this function is very nicely convex function. Okay. 1 by x is also convex, but it's not defined for negative numbers. Okay.
Okay.
I will check it out. I think it's a very nice suggestion. I can use it. Okay. Maybe that there is another reason for that. Okay. I'll check it out. Okay. And we'll let you know in the next class. As far as I know, it is not defined for negative numbers, and that is the only reason why it is not used. So in this case, the function would have been 1 by g of y I hat. Okay. And there may be a lot of differentiability issues with that. Okay.
Yeah.
So that would be one of the reasons why it is not preferred, because 1 by x, if you differentiate, it becomes minus 1 by x squared.
Yeah.
Okay. So it becomes the square of it. This does not become that.
Okay.
This does not become that. I'll talk about it. What is the differential of it? Okay. This does not become that. Okay. Similarly, if you look at on the right hand side, don't you think this is just this function only, but shifted by 1? Yes or no? This is just this function only, but shifted by 1.
Yes, sir.
It's a mirror opposite of it, right? So I can write it like this. 1 log of minus of log of 1 minus g of y I hat. See, if you're not convinced, let's check it out. Okay. If g of y I hat is 1, what is the outcome? If g of y I hat is 1, what is the outcome? Minus of log of
0.
0. What is log of 0? Minus infinity. Minus of minus infinity is infinity.
Plus yes.
So do you see that now at 1 it touches infinity? Does that make sense? Yes, people.
Yes.
Is this clear? So do you understand how these loss functions are designed? Okay. So the beauty is we have to have a convex function and a differentiable function. Okay. And now I'm going to show you how to combine them, since we have two different loss functions. Okay. So you can put it like this. If you have a sample whose actual value is a 1, see, I will have so many samples in my data set, right? Whose actual value is a 1. Can I say that for all of them, the loss function is this? For all of the samples, let's call it as N1. Okay, let's call it as N1. If there are N1 samples in my data set with the actual value is a 1, their loss function would be minus of log of g of y I hat. Does this make sense? Because there will be many, many samples, right? Not just one sample. I just defined it for one sample. This is how you measure it for that sample if you are incorrect. If you had many samples, you will measure it as the sum of all of that. Okay. And for all of those samples whose actual value is a 0, the loss function is this. Okay. Let's call it as N2 if you have N2 samples. N1 plus N2 is equal to N. Okay. In total. So minus of log of 1 minus g of y I hat. Okay. I'm going to show you how to combine these two loss functions. Let me just first write it and then I'll explain. Okay. I'm going to merge, let's call it as say L1 and L2. These are two loss functions that I'm going to merge. Okay, let's see. I'm going to write it and then we will discuss. Okay, this is the loss function. All right. Okay, so what are the possible values for yi? Any given sample, what are the possible values for it?
0 or 1.
0 or 1.
Zero.
Okay, let's take the first value as 1. Okay, you can see there are two components, right? This is term 1 and term 2. So which term goes to 0 if which term does not contribute if your actual value is a 1?
Second one.
Term two
This
is
will go
zero.
to 0, right? Because 1 minus yi will become 0. Okay, now if you put yi is equal to 1, what is this becoming? Minus of summation of log of g of yi hat. Do you see that now?
Yes.
That is what you want, right? When the actual value is equal to 1, that should be the loss. Okay, now let's look at it from the other perspective. Okay, when yi is 0, which term gets eliminated?
First.
The first one. Put yi as 0, this will become 1. So log into, sorry, there is a minus sign involved outside. Don't forget this minus sign. Okay, minus of summation of log of 1 minus g of yi hat. Don't you see that we are using this? It's a very beautiful way of combining two different loss functions. Okay, is this clear? Yes, people. So at a time, only one of the functions is active, and that is what we want, right? Because it can be either 0 or 1. So for a given sample, it can be either 0 or 1. So only one term should contribute, right? And by the way, you should know that sum of loss functions is also a convex function. Sum of convex functions also gives you a convex function. So for every sample, it is convex. So if you combine the convex functions, it will also give you a convex function. Okay. So overall, this function is convex. It is differentiable. Log, as you know, is differentiable. Okay. So this is differentiable. So let me rewrite this again, and you guys will tell me a few other things about this loss function. Okay. So you have almost understood everything. But perhaps it is, are you able to follow the maths, or is it too difficult for some of you? Are you able to grasp it? Like some of you at least, can you say a yes if you are able to grasp it? To some extent at least.
Actually, I
To
have
some
math
extent,
background.
not completely. To some extent.
To some extent, right? So if you just revise it, right, you'll probably get more out of it. See, nobody is going to go into that detail from your interview perspective. Since you guys asked, you want to know convexity of it. I'm discussing all these details. Okay. Otherwise, I would have just told you, okay, use this function. This is convex, differentiable. Go with it. Okay. Now, so we have seen, okay, this function is convex. Okay. We have visualized it as well. Okay. Now, my question is this. Do you think this function will ever become negative? This should tell you, by the way.
No.
This will always be positive, right? Even though there is a negative sign in front. Okay. Negative is done to ensure that it comes out to be positive. Because each of the individual terms in this brackets, okay, it is negative. So negative of negative makes it positive. Okay. All right. So this is the error. Okay. Error is always positive. Please remember this. We talked about this in the very beginning. Error functions are always positive. Loss is always positive. You cannot say loss is negative. Okay. So what is it that I should do? I should minimize it or maximize it? It's a loss function.
Minimize the loss.
Minimize the loss function. What are the parameters? Yes, people, what are the parameters? Thetas. So if you have d features, it will go up to theta dx di. Okay. Sorry, I should write it like this. This is your yi hat. And g of yi hat is 1 divided by 1 plus e to the power of this minus yi hat. Okay. So we are trying to minimize this with respect to all the thetas. Okay. Is this clear? This is the loss function that you're trying to minimize. Okay. Now, there are some special names for it. This is also called as binary cross entropy. this function has a name which is called as binary cross entropy function. It is also called as the log loss. Another name for it. Okay, another name for it. So when you are doing this method, you are trying to minimize the log loss to obtain the thetas. Okay, unlike in linear regression where you are trying to minimize some form of sum of squared errors. You're trying to minimize ordinary least squares, mean squared error. You can use any of that. So here also you can use any of that. Okay, just a few things. Okay, this component is responsible for class 1 or class 0. First component.
Last one.
Class 1. Okay, this is the loss for class 1. And this is the loss for class 0. Okay. Now, I'll just ask you one simple question. Let's say if I multiply this loss with, say, W1 and this with W2. Okay, W1 is a constant and W2 is also a constant, which I will pre-specify. Can I say that W1 tells me the loss, I'm giving more weightage. Let's say if W1 is greater than W2, can I say that I'm giving more weightage to class 1 samples?
Yes.
Okay. So you can think of giving more weightage to a particular class. To which class you should give more weightage? Okay, let me ask this in a simple way. When you are training an ideal model, okay, when you're training an ideal model, do you want the, and you're trying to do binary classification, do you want the samples to be equal or biased in favor of a particular class, like more samples for one class and very few samples for the other? If your objective is to train the ideal discriminator, do you want to be equal or do you want it to be biased in terms of the number of samples?
Equal, right?
Equal, right? So that you can get a good discriminator. Spot on. Okay. Now the question is this. In most real world data sets, what do you feel? They will be equal.
No.
Let's think of any data set. Okay. So let's say majority class is that one which has more samples. Okay. Majority class, we typically use the term majority class for that particular class which has more samples. Okay. And minority is the class which has lesser samples. Okay. Relatively lesser samples. So for which class I should give more weight? Majority or minority?
Majority.
No, majority is
Minor-
more in number, right? You should give minority more weight. Okay.
Minority.
It should be minority, right? If you think about it, because this summation, it is running on all the samples. Which class is coming more times? The majority class. So it is already having more weightage.
Yes.
The minority doesn't. Okay. So that is why we give more weightage to the minority class. So when you have something called as an imbalanced data set, imbalanced data set is the one when the number of samples are very, very skewed in favor of a particular class. Okay. So there you try to give more weightage to the minority class. Okay. Give more weightage to the minority class. That's a key takeaway from this loss function. Okay. Now, another thing to add to this is this. So people use gradient descent to solve it. Just a second. Sorry for the inconvenience, guys. Okay. So we have this imbalanced data set with us, okay, and you can give, in that case, you can give more weightage to the minority class. Okay, you can give any number. Okay, you can be giving 10, 20, 30, 40, doesn't matter. It will just increase the loss. Okay, it's a constant number which adds more to the loss. So whichever class has more weight, that will be given more focus on. It will be focused more upon to give you the better thetas in favor of that. Okay. All right. Now, this function, don't you think it can overfit as well? Just like linear regression, do you think it is possible the thetas that you get, they are good for the train set, but not good for the test set?
Yes.
That is also possible here, right? So don't you think I can add penalty functions to it? Yes or no? The same way with what I did with linear regression and multiply with the lambda, the alpha in implementation. So if you remember all of my previous sessions, you'll be able to follow everything. And what are the different penalty functions that we discussed?
Ridge regression, lasso, and elastic net.
Ridge, lasso, and elastic, right? They are the names. So when you are using linear regression with L1, then you call it lasso.
Okay.
When you are using linear regression with L2, you call it ridge. Okay. But the penalty functions name are what? L1, L2, and elastic net. So you can use those penalty functions here as well. Okay. See, when you are minimizing this term, right? I equals to 1 to n yi minus yi hat whole square. You can put a 1 by 2 also outside, it doesn't matter. And you say this is it. Okay. Sum of the theta j's. This is actually called as lasso. Okay. And this is called as L1 penalty. Okay. You multiply this with lambda. Okay. So this is called as L1 penalty. This is only called as L1 penalty. So I'm saying you add this L1 penalty here also. Okay, you add this L1 penalty here also. So you can add L1, L2, elastic net. All three can be added. Okay. How it is this solved? This is optimized using gradient descent. This is optimized. This cross entropy loss is minimized using gradient descent. So you use gradient descent to optimize it. You use gradient descent to optimize it. I'll just rub this so in case you don't get confused, okay, with this. So you use gradient descent to optimize it. Okay. By the way, people in the implementation, right, you will see that there are advanced variants of gradient descent. So don't get bogged down by the names. Okay. So you use variants of gradient descent to optimize it. So you might see variants like conjugate gradient descent. You might see Hessian based methods. Just giving you the names right now. So when you see them, okay, don't get bogged down. The purpose is not to discuss how they work. If I discuss it, I require at least 30 hours just to discuss the optimization algorithms. But what you need is only gradient descent for now. Okay. Now, these methods, I mean, this method which minimizes this cross entropy loss. Okay, this has a name. This is called as logistic regression. Please note that you are doing regression only. See, okay, what are we finally determining? Anybody? What are we finally determining? If I give you a sample, what will you predict? You will predict between
Minus infinity to infinity.
and you apply the sigmoid on top of it. So what is the final resultant? Between 0 to 1, right? Can I say, even though it is a value between 0 to 1, it is a real value?
Yes.
It is squished in the range, right? So you're doing regression. Yes or no?
Yes.
Hence the name logistic regression. The log function, right? That is a log loss. The logistic comes from that. Okay. So we are still doing regression, but what is this used for? For classification. Okay, for classification. Okay, and now I'll just talk about this one thing, and this is the last thing about this algorithm. One more thing is there, maybe at the end. Okay, so you know that for any sample, I figure out theta naught plus theta 1 x1i plus theta 2 x2i. And let's say if you have d features, I'll go up to theta d xdi. I put the values in x1, x2 for the input. Okay, I'll get a real number. I applied sigmoid on top of it. I get a value between 0 to 1. I get a value between 0 to 1. My question is this: how do I predict? If it is greater than what? I say it is 0.5. If it is, if it is greater than this threshold, I say it is class 1. Otherwise, it is class 0. What is the threshold?
0.5.
0.5. So threshold is 0.5 typically. So can I say when g of yi hat is equal to, or I'll simply write it like this, when g of y hat is equal to 0.5, this should be the equation of my separating line? Yes or no? Whichever threshold that you pick, all the samples on that line will have to be equal to 0.5, right? You will not be able to tell. So let's try to figure out what is that equation. What is g of yi hat? This is theta naught plus theta 1 x1 plus theta 2 x2. And I'll write it like this. Okay. Okay. I'm going to do just one change to it. Please see to this. So I'm going to say theta naught into x naught I, where x naught I is always 1. Where x naught I is always 1. Okay. So g of yi hat can be written as, one more thing, this whole thing can be written as, see to this carefully, j equals to 1 to d, theta j xj. J is equal to 0 to d. Do you think I can write it like this? After I multiply with theta naught with x naught I. Okay, this simplifies it, right? Where x naught I is always 1. Okay, where x naught I is always 1. Okay. All right. So I'm going to use this equation to simplify it instead of writing the whole thing again and again. So this is 1 by 1 plus e to the power of minus y hat equal to 0.5. Okay. 1 by 1 plus e to the power of this minus y hat equal to 0.5. Okay. 1 equal to 0.5 into, sorry, plus 0.5 into e to the power of this minus y hat. Take this 0.5 to the other side. So you get this, cancel it out. And you can write this 1 to be e to the power 0. So y hat becomes equal to 0, or minus y hat becomes equal to 0, or you can simply say y hat becomes equal to 0. And what is y hat? Theta naught plus theta 1 x1 I up to say, you can simply say theta naught x1 plus theta 2 x2 and so on till theta dxt is equal to 0. Do you see the difference between this equation and the one that we got from linear regression?
Yes,
What is the difference?
that was equal to 0.5 and this is
0.5, and this is equal to 0. Okay. So can I say that if I give you a sample which is say A1, A2 up to AD, so you will put A1 here, A2 here, AD here, and if you get a value higher than 0, what would you assign it as? This is a separating line. So if you get a value higher than 0, what will you assign it as?
1,
1, otherwise it will be
0.
0. So if the real value is going to be greater than 0, it is class 1, otherwise it is class 0. Okay. If the probability is what? Okay, let me just ask you this. What do you think? Okay. Okay. What do you think the value is? So you told me, right? If this thing comes out to be equal to 0.5, okay, I cannot say. What do you think the value of z is in that case? What is z when you cannot say?
E to the power minus z should be 1 in that case, so z would be.
So what is z?
I'm not good with exponents, so z would be 0.
This should be 1, right? That's what you meant,
Yes.
right? Okay. Don't you think I can write this as e to the power 0?
Yes. That is
Yeah.
And what do you think we got?
yes.
Z is equal to 0. That is where we cannot say, right? Okay. So this should have given you a hint that the equation of the line is where the real number is equal to 0. You say that, okay, we cannot make a statement. If it is greater than 0, we say it is class 1, otherwise it's class 0. If the probability is equal to 0.5, we cannot say. If the probability is greater than 0.5, we say it is class 1, less than 0.5, it is class 0. Okay. So you can make a comment about real numbers also, and now you can make a comment about probability also. Okay. All right. So this is your logistic regression. Very, very simple algorithm. You can make curves with it as well. Just generate polynomial features and you will have different types of curves. Okay. Find out the optimal values of your alphas if you are doing regularization. Okay. So you can do a grid search on that. You will do all of it in the next class. Let's discuss a few other things. Okay. All right. Now I want to discuss this next algorithm called as support vector machines. SVMs for short. Okay. See, this algorithm can be used for both classification and regression. I'm going to first discuss it for classification. Okay. Logistic regression, even though it's a classification algorithm, but it does regression internally. Okay. It's a variant of linear regression, you can say. Okay. All right. Now, I want to go back and maybe show you some similarities that it has with logistic regression. It is kind of a generalized logistic regression. Okay. Okay. I want you to focus on this loss function. can I say that the final thetas that I get, the final d-dimensional hyperplane that I get, it is dependent on all the samples? Can I say every sample contributes towards the thetas? Yes or no? There's a summation involved outside, so that should tell you. So every sample contributes. Now I'll go back to the example that I started with. Okay, look at this data. Okay, or maybe I'll make another one. Okay, maybe I'll make another one. Okay. So please note that this is also a binary classifier, just like logistic regression. It's an extension rather. Okay. So let's say these are the points. I'm going to circle some points. Okay. So your objective is to get this line which separates x's and triangles. Okay. My simple question is this: if there was a triangle here, do you think this triangle should contribute towards the line, towards the orientation of this line?
Not required.
Not necessary, right? So every point, I mean, currently it is sharing the same weightage in logistic. Okay, what about this point? Should it contribute highly or not?
Yes.
Yes.
Okay,
I-
and what about this point?
Right.
Yes.
Even this, they should contribute more, right? Which are closer to the boundary. So can I say that the points which are of belonging to the opposite classes, and if they're close by, they should contribute more?
Yes.
Okay, that is the idea of support vector machines. Okay, so unlike in logistic regression where everybody contributes, in support vector machines, only those points contribute which are close by. Okay, the other, the beauty of this algorithm is, see, I'm not going to discuss this algorithm with theory, derivation, no, nothing. Okay, I don't have the bandwidth for it. If I do that, I require at least 8 hours just to discuss the derivation of it, frankly. Okay, so what I'll give you is this intuition, why this algorithm is so popular and how you can determine the support. Nobody is going to go there. They'll ask you, okay, what's the derivation? I'll tell you what the loss function is if you just want to remember the name. Okay, so how this function changes. And the beauty of this support vector machines is it can automatically determine which are the points that should actually contribute. You don't have to manually specify. The algorithm will itself automatically determine what are the points, and it will determine the line also. That's the beauty of this algorithm. It's very, very intricate. Okay, I mean, if I do that now or maybe in the next class also. So probably what I'll do is, if I'm able to cover everything till the end, okay, then I mean, obviously I will take extra classes also if I'm unable to cover anything. At the end, so today obviously I'm not able to cover this. It requires at least 6 to 8 hours for sure. Okay. What I'm focusing right now on is this. If at the end, I'll try to cover this at the end. If we have 2 hours or at least 3 hours remaining till the end, I'll cover it. Otherwise, I'll share some material where you can have the derivation and the understanding of it. Okay. I'll give you some insights like how you can understand the derivation. I'll probably spend 1 hour to do all that. Okay. But for your information right now, you should know this, that the points which are nearby, they are called as support vectors. Okay. They are called as support vectors. Okay. Another key difference between this algorithm and logistic regression is that the labels here are 1 and -1. They are not zeros and ones. Okay. And the equation here is also theta naught plus theta 1 x1 plus theta 2 x2 is equal to 0. So anything greater than 0 is going to be +1. So all these samples are +1s and all these samples are -1s. That's one more difference between logistic and support vector machines. Why they say it is +1s and -1s? Again, if I tell you this, it requires mathematical derivation. Okay. So, okay, maybe in the next class, I'll try to describe everything related to support vector machines. Is it okay if I take, say, 4 to 6 hours just to describe this? Or would you want to read it on your own?
You can share the material links or some videos that can.
Okay, no. If I share the video, then again, I'll be bombarded with a lot of questions. So it will definitely take me time. Okay, what I'll do is I'll keep it at the end. Okay, I'll keep it for the end. So in the last class, I'll try to describe everything in the limited time that I have. For the nitty-gritties, I'll ask you to cover like after those 2 hours. Okay, if there is something that you can read and you can understand it on your own, then I will say, okay, you can read this and this is easy to understand. Okay, if something is not easy, I'll cover that. All right, I'll ensure that you know about SVMs. This is where everybody gets stumped. This goes over the head. Okay. So if you have been able to follow me up till now, if I describe SVMs, you will not be able to follow. Pretty sure. Okay. It raises a lot of questions as well. Okay. The way it determines the important points, the support vectors. How does it determine this optimal line? What are the different loss functions that you can use? And how does it do non-linear classification? So currently I have a linear function, right? So just to explain that non-linear concept, right? Maybe you guys try to read on your own and then probably you will realize, okay, why it is so difficult. No, I can do that, okay, but I need 6 to 8 hours to do it. It's not something that I can do it in a matter of, and this topic has been given just 10 minutes. Okay, so maybe the CUVI curriculum has been designed just for, just from the data science perspective, as in the implementation perspective. So they thought maybe keeping logistic regression and SVMs in the same module is okay. Okay, it's not okay. All right. When I teach this in my course, I take at least 8 hours to cover this. And when I say 8 hours, I'm being modest. Okay, there are courses on SVMs. Okay, there are courses on SVMs. Okay. So we'll discuss SVMs in detail. It's also a binary classifier. Once I discuss the classification, I will tell you how it is discussed. I mean, how it is used for regression also. So this can only be discussed once you guys know how to do it for classification, because they are extensions of each other. It's not very straightforward. Okay. Or maybe I'll give you the motivation, and then with that you can explain, okay, how it can be used for regression. Okay. So let me tell you what SVM actually does. Okay. So if this is the 2-dimensional points, okay, let's say these are some of the x's, just make it below some of the x's, and these are some of the triangles. So what SVM does is, okay, so imagine you have the tightest cylinder, okay, you have a tightest cylinder, and the cylinder is like this, and cylinder is like this. So imagine you have 2 parallel lines, okay, and you have 2 parallel lines, you're trying to expand these lines. Okay. So as soon as these lines hit these triangles, okay, you stop. Okay. As soon as you hit these x's, you stop. So you're trying to just expand it. Okay. And then you will move around this cylinder according to the best fit. Okay. So you are allowed to move this cylinder. Okay. This is just a visual representation of it. Now, let's say this is the tightest cylinder that I can have. Okay. Or this is not the tightest. Maybe say this is the what we call it as the biggest cylinder that I can fit between these points. Where do you think the best separator would lie? Where do you think the best separator would lie?
Center of the cylinder.
In the middle of it. Okay, in the middle of it. So this is the best separating line that SVM gives you. Okay. This line is theta naught plus theta 1 x1 plus theta 2 x2 is equal to 0. What do you think the equation of this line is? Any guesses? I told you the labels should tell you this. Theta naught plus theta 1 x1 plus theta 2 x2 is equal to +1. This is theta naught plus theta 1 x1 plus theta 2 x2 is equal to -1. Okay. So the one in the middle is equal to 0. Okay. So I'm just giving you some mathematical details. These points that I've highlighted, right? These are called as the support vectors. Okay. These are called as the support vectors. Okay. The beauty is it will determine the support vectors. It will determine the best fit line on its own. Okay. And the loss function which it uses is called as hinge loss. We'll talk about it when we discuss the actual optimization. Yes. Okay, at least the motivation is clear, right? What it is trying to do. So you can say it is trying to draw two parallel lines and ensure that these two parallel lines. So please note that these parallel lines are, I mean, can you see that from the equation, these lines are parallel? Can you see from the equation, these lines are parallel? Only the intercept terms are different. One is theta naught minus 1 and one is minus of theta naught, minus 1 minus theta naught. Yes or no?
Yes.
In maths, let's say if I give you this line, a1 b1 plus a2 b, let me just write it like this. a1 x1 plus a2 x2 is equal to 1. And the other line is say a1 x1 plus a2 x2 is equal to 3. Are these lines parallel?
No.
Yes, people. Are these lines parallel?
No.
Yes. They are.
Yes, yes.
Only the
Yes.
coefficients are different. Okay. The coefficients are the same. Only these terms are different. And what are these terms? They are the intercepts. So one of the lines is hitting -1 and the other line is hitting -3.
Yeah.
Okay. So that's how you can say, okay, these lines are parallel. So what SVM tries to do, it tries to fit two parallel lines instead of one line. And why it is so beautiful is that, okay, I want you to realize this. If I use this top line, if I use this top line as my classifier, as my discriminator, do you think with this line also I'll be able to do a good job? So anything on or above is going to be triangle. Anything below is going to be an X. Yes. Okay. Think about the line which is at the bottom. Anything on or below is going to be X. Anything above is going to be a triangle. So are these two lines also good separators?
Yes.
And the one in the middle would be the what? The best. So it does actually better than logistic also in most cases. See, I'm giving you these, slight, very, very you can say intrinsic details. Writing these details in mathematical format becomes very, very difficult to digest. Okay. So that's why I'm not discussing it right now. We'll do it at the end so that when you have seen everything, right, you should be able to follow this derivation also. But this derivation is completely different from everything that you will see. Okay. So I don't even encourage you guys reading about it on your own right now. I'll cover it for sure. Okay. I will not leave it. I promise you that. Okay. However, just digest this fact that, okay, this algorithm is going to give you these support vectors for now. It will automatically determine these vectors. It will give you the indexes of those points, which are the support vectors in the implementation. Okay. And we will also see how to do non-linear classifications with it. The beauty of this algorithm is, okay, let me show you one data set, which is like this. One data set, which is like this. Okay. And let's say the triangles are outside. Do you think if you use any model based on linear regression, even if you have polynomial features, would you be able to generate a decision boundary for this?
No.
I mean, whatever model that you use, right? Curvilinear, parabolic, it will not work. Okay. But this SVM can even separate this type of data, like concentric circles kind of thing. It can actually determine this kind of a boundary also. So it will make two concentric circles, which are kind of concentric, and the one in the middle is going to be the best separator. Okay. It can do this, but you require one more technique, which is called as kernelization. We'll discuss kernelization. It's fairly advanced. Frankly, trust me, it requires your brain to be so much active at that time just to understand it. Okay. So we'll discuss it at the end. So SVMs with kernels, they can help us achieve very, very highly nonlinear decision boundaries. Okay. And how it does it, I'll just give you the motivation for it. So what it will do is it will try to project this data. You need projection concepts also. Okay. It will try to project the data into high dimensional space. Okay. So currently, what is the number of dimensions right now? Currently, what is the number of dimensions right now? Two, right? Two features. Okay.
Yeah.
So what we'll do is we'll project each point into a high dimensional space. The number of dimensions could be 3, 4, 5, sometimes infinity. That is where, okay, yeah, we will talk about it, like how to do that. Don't worry. Okay. So, okay, think about this. Can you think of a particular figure whose projection is like this? Can you think of a three-dimensional figure whose projection will look like this? Can you think of a 3D shape whose projection is going to look like this if you look at it from above?
Cylinder.
Let's say cylinder, okay. Maybe a simple shape that you use in your kitchen.
Flat.
A bowl. Any
Yeah,
bowl. Look at this, okay. Imagine that. See, my drawing is bad, okay. All right. So imagine this is a 3D. I mean, we are in the 3D space, okay. All x's are on the bottom. Okay. The bowl shape is like this, right? It expands as it grows. Okay. And on the surface, you have these triangles. Are you with me if I look at it from the top? Are you with me if I look at it from the top? My
Yes.
projection will be the same as this. Yes or no? Okay. Now, what SVM does with the help of kernels is it will project this 2D data onto this 3D space. And can I say that in 3D, this data is linearly separable
Yes.
with the help of a plane? Okay. That's what SVM does. Okay.
Awesome.
Okay. Like the maths behind this is so lovely. Okay. If you appreciate maths, you will love this algorithm. This is my favorite algorithm in ML, frankly. Okay. But when I teach it, I get, you can say, weird eyes. Why we are doing this? Okay. I mean, couldn't you have, told us like, okay, let's just do the implementation with not telling us all these details. Okay. Maybe we'll see the details as well at the end. Okay. For sure. We'll see the details at the end. And I'll show you, okay, how mathematically with examples also, how you can project any data onto 3D, 4D, 5D or any space. And even infinite spaces. That's the beauty of it. Infinite. I said infinite spaces. So you can project it onto infinite spaces, uncountable dimensions. In the hope that okay, my question is this. Currently, you can see the data, it is in 2D, right? Yes or no?
Yes.
Okay. If I go to more than 3 features, would you be able to visualize it? No, right? Yes or no? If I give you 4 features, would you be able to visualize it? No, right? So if you cannot visualize it in 4 features, 4 dimensions, would you be able to tell, okay, that the data is linearly separable or not?
No.
You can, by the way. How? Fit a linear model to it. If the data is 100% accurately separated, can I say that now? See,
Yes.
by looking at it, I cannot tell, right? But I can fit a linear model to it.
Yes.
Okay. And then I can tell, okay. Then I can fit maybe say a parabola to it. And then I can say, okay, if it was separable or not.
Yes.
With the same concept, you have these different forms of kernels. You have different kernels. So one kernel will project it to 3 dimensions. Like given whatever number of dimensions, it will add maybe 2 or 3 more dimensions to it. Some kernels will add infinite dimensions. Okay. When I say infinite, you will be wondering, so how infinite? It should be countable, right? No, it will be infinite. Okay. That's the beauty of maths. Okay. We will talk about it in detail. Okay. So it will project the data onto infinite spaces in the hope that it is linearly separable there. Okay. So we will see all of that and how it does it, how it makes use of the different kernels. Okay. So this is the idea behind SVMs. I will just stop with one more explanation, how it is used in the context for regression. Okay. Let's see this. I'm showing you for univariate. Okay. So currently, when we are doing regression, right? When we are doing regression, my goal is not to separate. My goal is to best fit. Okay. Let's say this is the data that we have. Okay. This is the data that we have. My goal is to find out this best fit line, which would probably be like this. Okay. My question is this. Can you use the same analogy of fitting a cylinder? So there the objective was to fit the tightest cylinder, which can separate. I shouldn't say the tightest, it should be like the biggest cylinder that can separate. Okay. What should be the analogy here? You want to find a line which is encapsulated in a cylinder, which best what? Okay. What do you think the support vectors will be here? Okay. Do you think that each point should contribute? Okay. Do you think that, okay, let's say if this is the line, should this point contribute towards this line? It is the
Yes.
best fit line. No, you haven't understood regression then. Okay, think about which points actually contribute more when you are trying to fit a regression line. How do you
Sound.
this line? We try to minimize the sum of the distances. Sum of distances, right? Square of the distances. So if a point is lying on the line, is it actually contributing?
No, sir.
If a point lies on a line, does it actually contribute?
No, because it's 0.
It doesn't. So which point should actually contribute more? The ones which
Nearest,
furthest
Sir.
away.
farthest, yeah.
Okay. So where do you think I should make a cylinder? Here. So you can now think that, so in this case, I would say you are trying to make the tightest cylinder. So you are very far away and you are trying to bring this. Okay. So only those points which are on the outsides, on the outskirts, okay, these will be your support vectors. My drawing is bad, but again, this line L1 and L2, they are still parallel. Okay. The line in the middle is going to be the best fit line. It's the opposite of classification. Here, my job is to find out the best fit. There, my job was to separate. Here, my job is to squish. Okay. So I should say this is the tightest fit. This is like the, it's the opposite of it, like the biggest cylinder that you can have. Okay. So do you understand how it can be used for regression? At least visually. Is the idea clear? So we'll see how these thetas are determined from this line. So here the equation would still be theta naught plus theta 1 x1 plus theta 2 x2. This is your y hat. Sorry, in this case, just theta naught plus theta 1 x1, not theta 2 x2. Just one dimension is there, right? Okay. Sorry. So this is what it will be. All of these are interconnected, whatever you are studying, okay, they are all interconnected. So if you can appreciate the maths, you'll be able to crack the interviews very, very quickly. Okay, I'll stop here. If you have any questions, we can discuss. Any questions as such? Tomorrow will just be the implementation day. Tomorrow and day after, probably. Yes, any questions as such? Abdullah, you're trying to say something, or maybe there is, your mic is on and it's fluctuating. Any questions?
Sir, I'm from math background. Okay.
Yeah, okay.
Actually, I did MS in mathematics.
Oh, great.
So-
Then are you able to follow me? Like,
Yes, sir. To be honest, actually, I have some personal work, so
Oh.
I didn't. So I'm going to watch all the videos from the beginning. Actually, I watch your videos, but sometimes I had some what to say. I have some personal work, so that I
it's okay.
have some break.
You can ask me any number of times in between. Okay.
Sure, sir.
All right. So don't shy away. And now that I know that you understand maths, right, you'll be able to cherish it more.
How is it going to help me, sir? The machine learning.
Use, right? The only thing that they will ask you is the maths in the interviews. Trust me.
Okay.
If they're going to talk about ML, right, they would want to know, do you actually know how support vectors are determined? Do you actually know which kernel is going to project the data in, say, 2 more dimensions in comparison to some other kernel? Which hyperparameter should I tune? So if you don't know about those details, that all comes from the maths. Okay. So they will not ask you, okay, show me the implementation for SVMs. It's just a 3-line code. And you import SVM, you do fit and predict. That's it. Okay. But you want to know, right? Like how to, fine tune the SVM. So all that is there, right, is intrinsically involved here. And what I'm teaching you right now, when you join a company, they will ask you to read papers, research papers. And all of that would help you there. All of that. All the maths that you're learning right now, trust me, this would be the only thing that will be useful in your industry life when you're dealing with ML. Implementation would be just, you can say, your routine job. Understanding everything is very, very crucial to understanding. Understanding maths is very crucial to understanding the working behind these algorithms. If you just, I don't think it is easier just to remember, okay, if I just tell you, okay, go read about this kernel and digest this as a fact, okay, if you use this kernel, it gives you, say, these many dimensions. If you use alpha, it'll have this much impact. So if I tell you, do you think would you be able to remember everything without knowing what it does?
No, sir.
Right. I mean, so you're connecting the dots, right? If I do this, okay, what happens? If I do this, what happens? Okay.
Yes.
So when you read papers, you will see these connections there. Why they are designing a specific loss function? What are the problems if I do with a specific loss function and all that?
Okay.
You will appreciate it more like when you join a company and perhaps read more about the kind of research a company does.
Sure.
It's not as simple as just you applying these algorithms on a data set.
Mm.
There's a lot of thinking involved.
Sure. Thank you.
Yeah. Anyone would
But,
go on?
sir, but I don't know whether this question is right, but how are you so well versed in these many algorithms and so quick and clear?
Oh, I've been teaching this for 15 years and using it for probably 20 years now.
Oh,
I mean, not 15, 20. I mean, I exaggerated a bit, maybe say 12 and 15 respectively. I did my PhD in this area. So PhD, master's, everything, it was inclined towards this. I work in niche areas of ML. So I wouldn't say I'm an expert, but no. I mean, I have spent my fair share in similar areas and along these areas also. Okay. And I use it in my day-to-day life. Okay. And I actually train AI and ML professionals in this area. So I can tell you what they require.
oh,
I mean, you will become like me if you are able to spend some time on reading. Frankly, I'll tell you, I have personally read more than 15 books on ML.
oh.
If you read one, I'll tell you the name of the book. To this date, I don't understand the entirety of that book. Okay. If you can understand it, if you're from a maths background, right, you will have even more information than me. The book is called as Introduction to Statistical Learning by Trevor Hasty and Tipsharani. Okay. To this date, I don't understand some of the topics which are described there. It involves some advanced bit of maths, which is beyond even my comprehension. Okay. So I go to other books like Ethan Alpayden, Tom Mitchell, Christopher Bishop. That's where the topics are.
This is like never ending, like a sea.
It's maths only. Maths is never ending, right?
Yeah.
It's never ending. So it's like you can do the same thing by 30 to 35 different techniques. I'm not asking you to remember 30, 35. That's why I'm not going beyond gradient descent, right? Everything can be done with gradient descent as long as the function is differentiable. Okay. And that is where the crux lies. Most of the machine learning algorithms will try to ensure that their function is convex and differentiable. In some cases, you cannot make such a function. And that's where you encounter neural networks. But people still use gradient descent. How they use gradient descent is they have various different initialization schemes. So they will start with some different initializations and they will end up in local minimas. And then they simply see which local minima is the least. And they say that, okay, whatever I have obtained, I'm satisfied with it because I don't want to run it anymore. Because they cannot visualize the function, right? There are so many hyperparameters. You literally have billions of hyperparameters in neural networks, especially in state-of-the-art neural network models. But they still use variants of gradient descent techniques. Okay, so, but with the time you learn what are these variants of different gradient descent techniques. My job is to ensure that when you start reading on your own, you are able to grasp everything like this. Okay, but it requires a bit of reading from your side also. I mean, obviously I cannot cover everything in a matter of say 22 to 24 hours.
Yes.
I've been given around, I think, 20 hours. I'll try to take 24 to 26. But you need to invest some bit of time on your own as well. See, when you leave this curriculum, right, I can guarantee this, you should be able to answer all, maybe say 90 to 95% of the questions that are asked in the ML interviews. The remaining 5% which are difficult, probably you can explore. Because I don't know what someone asks, right? I can only tell from my experience what could be asked.
Yeah.
Okay. So that's
Can
about
you
it.
drop that book name in the chat box, sir?
Yeah, sure. So this is, so I'll probably upload these books if you want.
Yeah, okay. Thank you, sir.
Okay, I'll upload these books. Okay, don't worry. I'll give you maybe say 4 or 5 books. I think I've already uploaded some.
Yes, sir.
Okay. So I believe the elements of statistical learning is there. If you just search for introduction to statistical learning, yeah, I'll just write it. Okay, introduction to statistical learning. The authors are Hasty, Trevor, and Tibshirani. Okay, let me just write it like this. Okay, Hasty and Tibshirani. There are 4 authors. Okay, Tibshirani. It's a good book to follow, but it requires intricate maths. Okay, you need to be really good with probability, likelihood, distributions, if you want to follow this book. Otherwise, I suggest this book for everyone. Okay, Etham Alpaydan.
Okay,
It's
sir.
a very easier read. It's a very easier read. The book name is called as Introduction to Machine Learning. Etham Alpaydan. This is an easy read, comparatively easy read. For beginners, I recommend this, Etham Alpaydan. Okay.
Okay, sir.
Just to understand this book, Introduction to Statistical Learning, there is one more book called as Elements of Statistical Learning. 2 of the authors are the same. Hasty and Tibshirani are the same. So you need to study that first to understand Introduction to Statistical Learning. Okay. So I'm saying, okay, don't go buy that book straight away. Okay, first go with the Elements of Statistical Learning and then do this. Otherwise, you simply take Etham Alpaydan, and then there are many books. Machine Learning by Tom Mitchell. You have Intro to ML by Duda and Hart. Christopher Bishop book is also there, Pattern Recognition and Machine Learning. You have one more book by, I'm forgetting the name of the author. This is by Pearson Publications. I'll tell you one book which you can all probably buy if you want. There is this book by Sara Guido and Andreas Miller. This is Machine Learning with Python. It has all the implementation details. It's a good book to have. You can find the PDF online also. If you just search for it, you'll find the PDF online. Okay, it's Machine Learning with Python. It's probably CRC Press. Okay, so there you will not have all the nitty-gritties, but you will have all the details related to implementation. Okay, it's a good implementation book.
Yeah, thank you, sir.
All right. Okay. Yes, go on.
Sanatan, I have sent you the email what we were discussing yesterday regarding the ERPs.
Oh, I'll take a look at it because okay, just now or like
Half an hour ago.
half an hour ago. Okay, I didn't see. Sorry.
Not a problem.
I'll take a look at it. Okay, and I'll try to reach out to some connections and see.
Sure, Sanatan. And Sanatan, like since you're in the
Right.
In the battlefield, I can say, like, how is the demand and supply?
Oh, supply is actually very limited for good people. Demand is too big.
Okay. So like we stand
There
a
is-
great chance of getting placed.
You have a huge chance of getting based, frankly. Okay. So
No, because see, like the market works on demand and supply, right?
correct. See, the demand is actually very big. In most companies, there is a crunch.
Okay.
The only thing that I mean, what is restricting most companies to hire is so previously there was this I don't know if you are aware of these layoffs that happened.
Yeah, exactly.
Okay, so they happened because they kind of overhired a lot.
Yes.
And when I say overhiring, they hired for AI engineers and ML engineers a lot because there was this wave of this AI booming. Okay, and there were a lot of AIs which actually came out, like ChatGPT was there, Bard came out, Microsoft came out with a lot of like their own AI assistants.
Yes.
So, but when these companies realized, okay, after getting these models built, they realized, okay, there is not much that we need now from these developers. So all the developer jobs were gone. Developer jobs, not the AI and data science field. Okay, all the developer jobs were gone. So not all, maybe say, I mean, you still require humans, right? So most of the developer jobs were in danger, and so it will be the trend, but data is something that will be always there. So in terms of supply and demand, data science is something which will always boom. As we are collecting more and more data, we need more data scientists, more data engineers, more, I would say, these data analysts. So this is going to grow, but I believe there is going to be a upper limit on the salary that you will get.
Yes, because like when the availability is more, the rate per hour or like the salary what we get will be like
And everybody is now into this data science analyst.
yeah. In my apartment only there are 7 or 8 people doing the same.
So, so because there is so much competition, right? The negotiations become difficult. I mean, getting a raise is going to be a problem after a while, not right now, but after a while, it will be a problem. Like, I don't think data science salary would touch more than, so in the US, I'm talking about, it will not touch more than, say, 150K. That is like the highest level of data scientist that you can think of, maybe level 5, level 6.
Yeah, L5, L6, okay.
So nobody is going to touch even that 150K. Yeah. And 150K is a level 2 salary for a developer.
Okay, so Sanatan, can we aim at like L1 or L2 jobs? Like
You can target for L1, not for L2. The reason for that is, see, when you are looking at these senior jobs, right, what they ask you is a degree. That's the first thing. Degree, especially in a specific niche. For example, let's say if they hire you for building maybe say a ML product, you should have a degree in statistics. You should have a degree probably in related branches to AI. So they will look for niche people. And those are the people as they progress, right? They become L3, L4, L5. So when you join as L1, you will have a chance to, work as L2, maybe after 3 years. But directly you cannot join as L2, in my opinion. Okay, for companies, they will ask you for at least a master's degree or a PhD degree. Typically, when people go for, let me be very clear here. I think there is a big misconception that you can join as an AI engineer straight after your BTech or straight after your bachelor's degree or straight after, say, 12th. You can probably join as a data scientist, data analyst, not as an AI engineer or an ML engineer. If some company is giving you that, it's just a name. You are not doing ML engineers' responsibilities. You're not having that. Or maybe that company has a crunch. So you will be getting a salary of maybe 4 LPA. Just.
Okay. So the title would be different and the nature of work would be different.
Work would just be data analysis, and that too will be labeling and all. Okay, and they will
even my son can do if I teach him like for a month or 2.
They'll just want to entice you with the designation, but it will not be actually that MLE work. So typically when you join these big companies, right, they want you to do research. They want you to study. They want you to read papers and then see what is the state of the art, what is happening in the world. And they want that to be implemented on their products, not what you see in your day-to-day life. This is just the foundation that we are building. So as a fresher's job, yes, you will use all these things. But as the time progresses, you achieve, say, level 2, level 3 and beyond, you will see you will only do research-oriented work. Because any data set that you will look at, it will be new, not just to you, but for everyone.
Yeah, true. Like even for the management, it's like this is the emerging field, right?
In every field, it is, I would say being leveraged. Yeah, it is being leveraged by a lot of people.
Sanatan, like what would be the timeline for this industry to hit the top level and then stagnate? I'm giving it like 5 years.
No. At least 30 years, I would say it is going to be like this. It will probably see a boom.
Like, I don't know, like see like the present vertical where I am in, like it's already hit the stagnation level, like.
Oh,
and it's become like the run of the mill.
I wouldn't go that far, just 5 years. No. The dynamics are changing. I would say that we require more humans. And when I say humans, like good humans. Okay, people with good IQ. So the need is more actually. As we are building more and more AI related stuff, you also need to upskill yourself to keep, yourself competitive in the market. So if you just rely on like the basic fundamentals, it will become difficult after a while. Okay, you'll be stuck in that same job forever. If you want to upskill, probably you need to upgrade yourself. If you want to kind of get promoted, switch to different companies. So that is the need of the hour. See, to this date, I'll tell you, I spend 1 hour daily on exploring what is out there. Frankly, 1 hour daily.
As in with the latest updates.
I can tell you what I did yesterday. Okay, so I keep, kind of searching for more and more stuff, reaching out to my friends, asking them, okay, are you using these tools, or if there is something new in the market. And trust me, every other day, or maybe say every other week, there is something new.
So how do we catch up, Sanatan? It's like, see, like
You need to work.
no, like, see, like what my question here is, like, see, like you're saying, like every week something new is coming up.
Yes.
So how do I keep updated myself? Like,
So
like I cannot restart my system every day.
No, I'm not saying you have to install everything at every time, right? I'm not doing that either. Okay, so when you enter a particular, a company, right? Your primary work should be to work towards like the goal of that company, right? The objective, the task that is assigned to you. But you have some time for yourself also. In that time, you can prioritize, okay, these are some additional skills that I want to learn. So one of the things that I would recommend that that you guys should do, which is not a part of your curriculum, is deep learning. Please read about computer vision and all these things. You now have the basic fundamentals for it.
Okay.
See how you can leverage computer vision to build, say, simple, I would say, image-based or say speech-based products or speech-based applications. Okay, so at least some head start you would have, and then I will talk about, okay, you go to this company, download this pre-trained model and see how it beats your model by say 30% or so. Okay, so I can tell you about the state of the art and how your model is different from it. But like when you work in the industries, you do not have a limitation on the compute resources. As of now, you do. You cannot, you may not have a graphic card worth of say 256 gigabytes, right? That costs around 8 crore rupees.
So for that, we need to have the like environment and the infrastructure.
That is how the technology is progressing. People don't realize that like every day you get to see these new technologies, but they require huge amount of resources. I actually give this example every time. So do you know how much electricity was used just to train ChatGPT? Guess. In which state you are right now?
Me, I'm in Telangana.
Okay, so I'm also in Telangana. 5 times the electricity that is required to run Telangana per week. For a week, okay, 5 times the electricity that was required to train ChatGPT.
My God, that's like huge amount of.
Think about how many systems would it be. So it's not just about, so how long it would have taken them to ensure that everything would run smoothly. Okay, so that they are able to train on this. They would have to be very, very sure, okay, this is going to work. And it's not just that, okay, they train ChatGPT in 1 day. Okay, so the resources, we don't have those resources, right? So when you join these companies, only then you get to see, okay, this is what you can get. So ChatGPT, since everybody is using it, I just named ChatGPT. There are tools which are even, having more number of parameters than ChatGPT. They require even more time. Google built Bard. So Bard even took even more time than what ChatGPT did. It requires so much compute resources. So that's where this green energy, green revolution, sustainability is a big factor. So these people are working towards it. They're trying to reduce the number of parameters while still maintaining the same performance. So they are still researching and researching. Okay. And it's not going to change soon. Okay. It will probably take, advancements are happening at a very rapid pace, but this is, I mean, we don't have a silver line. Okay.
But the infrastructure is lacking.
Infrastructure is lacking. Yeah. I mean, that's why, I mean, you would have heard of quantum computing, right?
Yes, yes.
Transitioning towards that. But just to build a quantum computer for everyone, okay, currently there are only, I think, 2 to 3 quantum computers in the world.
Yes.
So IBM has one, and I believe Google has one, and there is one by Microsoft. I don't know if they have it in house or maybe some university has it and they are making use of it. But Google has one and IBM has one. So just to and it is around 16,000 crore rupees, the one that they have built.
Okay.
And it does simple, what we say is, it does a lot of calculations at a rapid pace, and that's what it can do. So it's like it is trying to solve those problems which were not feasible if a human were to do it, or if a simple computer were to do it. So they just solved something which they know can be solved. And if a regular computer were to do it, it would have taken probably, say, 20,000 years for a regular computer. And they did it, I think, in 1 day or something like that.
20,000 years, that's not even a lifetime of a single human being.
So that's why, I mean, there is this leap which is happening. I don't know when it would become, see, you know what, like when computers came, it took around 40 years for everyone to own a personal computer. From the moment of the advent of the idea to actually having a personal computer, it took 40 years. So when the first personal computer was built, and to the moment when everybody owned a computer, okay, it took 40.
That journey is 40 years. Okay.
The journey is 40 years. So having a quantum computer in let's say a lap of everyone, okay, I don't think it is even possible. Okay, I don't know, so much cost cutting, so much it requires around what should I say, 1,600 square foot just to
I
keep.
think these guys, this Microsoft guys, they host their quantum computer in MIT, if I'm not wrong.
So I know that there are actually 2 or 3 computers only, but no more than that. Maybe say 4. Okay, but no more than that. People are working on it, maybe in secret. So China people are, I mean, they will be doing it for sure.
We are ahead of everyone.
AI, which would be doing it for sure. Yeah. They are also a big name nowadays.
Yeah.
AI.
And Sanatan, one last question for you for today is like, say for example, like we are talking about the technical part. Say for example, like in the field where I am, we have like networking, software, and hardware. And is there something similar in this field also?
Yes, they are using a lot of AI to. So let's say if you are talking about networking, right?
Yeah.
Okay. A lot of AI can be used. So if you're thinking just from a marketing perspective, how do you, I mean, to which people you should reach out? Can you make something of, say, something like suggestive nature? Things of
the telecom providers.
Telecom providers, not just telecom providers. Let's say, okay, you want to advertise something. Okay. To which influencers you should reach out?
On the social media like WhatsApp, Instagram.
Okay, think about, let's say, okay, let's talk about these parties that are there. Parties as in these political parties. So we have 2 parties, right? NDA, BJP, and essentially Congress.
Right.
Okay, let's say they, so every 5 years or every year or so, like whenever the elections are happening, they want to select candidates, right?
Yes.
How do they find an appropriate replacement for the next year?
The guy who's got the big pocket.
No. Okay, they actually do a lot of stuff, not just with the big pockets. That's one factor. Okay, there's so many things that are happening. How do they turn the elections in a particular favor? Okay, that's all where AI is being used. You know that, like, it happened in the US elections.
Yeah, exactly. I was about to quote the same.
10 years back it happened. And now they have started using it.
In 2024 here also, I think.
It is happening. I mean, it is happening in front of our eyes. You see news channels. They are feeding you so much bullshittery every day.
Yes.
I can't see a single news channel which is not biased towards BJP. Okay. So all of this, I mean, people have realized, okay, data is the fuel, so they are kind of making use of it in the best way possible in the best of their interests. Yeah. So I'll stop here. Okay, maybe we can discuss about this. This is like
Yeah,
all
yes.
okay.
Thanks,
It's
Anand.
a
Thank you so much
philosophical
for your
topic.
time.
All right, Kiran, take care. Bye, everyone. I'll upload the slides and some these handwritten notes and the slides so that you can read about it. Okay. Bye, everyone.